the ancient world did not disappear completely. It left behind messages written in stone, buried beneath cities, sealed inside mountains, and scattered across landscapes where entire civilizations once rose and vanished. Some of these structures are so massive that their construction still seems almost impossible. Others contain chambers, alignments, symbols, and engineering details whose true purposes remain unknown. The deeper archaeologists explore, the stranger the evidence becomes. Foundations appear older than the monuments built above them. Stones weighing hundreds of tons rest in positions that modern machines would struggle to reproduce. Forgotten passages lead nowhere, while ancient designs seem to follow knowledge that was never recorded. Were these monuments created only for kings, gods, and the dead? Or were they built to preserve something their makers feared the future would forget? Every ruin is more than a remnant of the past. It is an unfinished message, waiting for someone to understand it. In Berbinzana, Navarre, northern Spain, near the Arga River, Las Eretas looks like a small Iron Age village. But beneath its stone foundations lies a question that is still not fully answered. How did a community more than 2,400 years ago build walls, streets, and houses with such practical engineering skill without leaving behind a single written manual? The site was discovered in 1991 when archaeological work revealed remains only about 1 metre below the surface. Between 1991 and 1996, excavations uncovered a fortified settlement with houses, a central street, defensive walls, towers, and domestic spaces preserved well enough to reconstruct part of the village in situ. Las Eretas is dated mainly to the 6th and 5th centuries BC, with its origins reaching back toward the 7th century BC, placing it in the Iron Age culture of the Upper Ebro region. At first glance, Las Eretas does not look monumental. It has no pyramids, no giant statues, no royal tombs. Its mystery is quieter, hidden in construction details. The village was fortified, yet it was also domestic. It had rectangular houses, some between 35 and 72 square meters, arranged along a central road and small open space. This was not a random cluster of huts. It was a planned settlement built with repeated layouts, shared walls, controlled access, and a defensive perimeter. For a small Iron Age community, that level of order suggests a kind of practical knowledge that archaeology can observe, but cannot fully reconstruct. The most intriguing feature is the wall system. At Las Eretas, construction was not based on one material alone. The builders combined stone, timber, clay, earth, and plaster into layered structures. The houses were rectangular and often attached to the defensive wall. Excavation reports describe dwellings with similar construction schemes, while later studies of Iron Age Navarra note walls with plastered interiors, sometimes painted white and decorated in black and red. These were not crude shelters. They were engineered living spaces, designed to stand, insulate, divide, and protect. What makes the walls especially mysterious is that they functioned almost like a composite system without the kind of mortar or cement we associate with later stone architecture. Stone provided weight and stability. Earth and clay filled gaps, absorbed pressure, and sealed surfaces. Timber or wooden frameworks could strengthen the structure while also allowing slight movement. Plaster gave interior walls a finished surface and probably helped protect the organic materials beneath. In modern engineering, composite structures work because different materials compensate for one another's weaknesses. Stone resists compression, wood can flex, clay can seal, bind, and regulate moisture. Las Eretas appears to show an ancient version of this logic, but without any written explanation of how the builders understood it. This is where the real mystery begins. A simple dry stone wall can collapse if its weight is not distributed correctly, A timber and earth wall can rot if moisture is trapped inside. A clay surface can crack if it dries too fast. Yet the builders of Las Eretas combined these materials in a way that created walls strong enough for domestic use and durable enough to leave a clear archaeological footprint after more than 2 millennia. The site's defensive wall, houses, street, and towers were preserved sufficiently for modern consolidation and partial reconstruction between 2000 and 2001. That preservation does not mean every wall remained intact, but it does show that the original system left enough physical evidence for archaeologists to understand its design. The unanswered question is not whether these people had advanced technology in the modern sense. They did not need machines, steel reinforcement, or mathematical blueprints. The deeper question is how they learned the correct balance between materials. Too much stone would make the wall heavy and brittle. Too much earth would make it vulnerable to rain. Too much timber would increase fire risk. Too little timber would reduce flexibility. Las Eretas suggests a building tradition based on repeated experiment, inherited memory, and close observation of failure. Somewhere before the village was built, generations of builders must have learned which walls cracked, which walls leaned, which walls survived winter, and which walls burned. The defensive architecture adds another layer. Las Eretas was a fortified village, not merely a farmstead. Its wall, tower, and controlled interior plan show that protection was central to the settlement's design. Archaeological interpretation describes the site as one of the early fortified settlements of the Upper Ebro area, with a morphology that remained influential for a very long time. This matters because defensive walls are not just thicker house walls. They must resist pressure from outside, define movement, and create psychological control. A wall around a small village changes the entire settlement into a machine of survival. Inside that fortified shell, the central street is equally important. Excavations identified more than one construction phase in the road, including an older pavement made with rounded stones and a later visible street surface of slabs. This means the village was not built once and forgotten. It was repaired, resurfaced, and modified. Roads are technical systems. They manage feet, carts, animals, rainwater, mud, and daily circulation. The existence of successive paving phases suggests that the inhabitants observed how the ground behaved over time and adapted their construction accordingly. Water control may be one of the least spectacular but most important mysteries at Las Eretas. The site stands near the Arga River in a valley with deep, well-drained soils, but a compact settlement of clay, earth floors, timber and stone still had to manage runoff carefully. Modern conservation work at the site included drainage and runoff control, which indirectly reminds us how vulnerable these remains are to water. In antiquity, the same problem existed in living form. Rainwater could weaken walls, erode streets, rot wood, and turn floors into mud. A village using earth-based architecture had to survive the climate not by resisting water completely, but by guiding it away. The mystery is how much of this was planned from the beginning. The houses of the first settlement were built after the stone wall and cobbled street had already been established, according to local archaeological interpretation of Phase 1. That sequence is significant. It suggests that the builders first created the defensive and circulation skeleton of the village, then inserted domestic life into that framework. In other words, Las Eretas was not simply a group of families building houses wherever they wished. It was an organized project. The domestic architecture also shows a sophisticated relationship between people and temperature. Rectangular houses with thick walls, small openings, earth floors, plastered interiors, and central hearths could store heat, slow heat loss, and create a stable interior environment. In Iron Age Navarre, where seasonal changes could be harsh, this mattered every day. The central hearth was not only for cooking, It was the thermal heart of the house. Heat rose, smoke escaped through openings or roof structures, and the mass of the walls helped moderate the indoor climate. No evidence suggests that the builders understood thermal mass as a scientific concept, but their architecture behaved according to that principle. Fire, however, was both useful and dangerous. Houses that used timber, clay, and thatch-like organic materials were always vulnerable. This creates another technical paradox. The same materials that made the walls flexible and insulating also created risk. Clay could protect wooden elements by covering them, slowing exposure to flame and oxygen. Earth floors reduced the spread of fire compared with wooden floors. Stone foundations could remain after the upper structure burned. If Las Eretas experienced destruction or rebuilding phases, each episode may have taught the community more about how to place hearths, thicken walls, and separate combustible materials from heat sources. The village also opens a question about measurement. Rectangular houses, repeated plans, a central street, and wall-aligned dwellings all imply a shared building language. Even without formal written plans, builders needed ways to keep walls straight, rooms usable, and plots consistent. They may have used ropes, body-based measurements, wooden rods, or simple sightlines. None of these tools would necessarily survive in the archaeological record. This is one of the great silences of prehistoric engineering. The knowledge was real, but the instruments were perishable. What remains is the geometry, not the method. The composite wall system is impressive because it served many functions at once, carrying loads, dividing spaces, supporting roofs, and protecting against weather, moisture, and daily wear. By combining different materials, each with a specific role, the builders created an efficient and adaptable structure. An example of practical ancient engineering rather than a single advanced technology. Located in Tucumán province in northern Argentina, the ruins of San Jose stand about 30 minutes from San Miguel de Tucumán, not as a lost temple of stone giants, but as a broken machine of mud, lime, brick, water, and forgotten engineering. The site was not uncovered in a single dramatic excavation. It survived in plain sight, the remains of a Jesuit mission and estancia known as San José del Monte de los Lules. Established on lands donated in the late 17th century, later functioning with a church cloister, houses workshops, a mill, a brick kiln, and agricultural production before the Jesuits were expelled from Spanish America in 1767. At first glance, San José de Lul looks simple. Brick walls, worn arches, collapsed rooms, and fragments of a colonial religious settlement. But the deeper question is not why it was built. The deeper question is why parts of it endured. This was not a dry desert monastery. It stood in a humid subtropical environment near the eastern Andean foothills, where summer rain, clay-rich soils, and seasonal water movement should have been enemies of old masonry. Modern climate records for nearby San Miguel de Tucumán show a strong rainy season. WeatherSpark records the rainy period lasting about 8.7 months, while other climate datasets place annual rainfall roughly around 900 to over 2,000 millimeters depending on station and method. That is what makes the remaining masonry so interesting. The walls were not protected by modern cement, chemical waterproofing, steel reinforcement, or engineered drainage membranes. Yet the old construction resisted generations of rain, humidity, biological growth, and ground moisture. The ruins were part of a productive Jesuit complex, not a ceremonial monument, and that makes the technical puzzle even stranger. Why would a frontier mission possess building solutions durable enough to survive in such a difficult climate? The most fascinating clue is the mortar. In historic masonry, mortar is not just the material between bricks. It is the hidden technology that decides whether a wall breathes, cracks, drains, absorbs salts, collapses, or survives. At San Jose de Lule, the old binder appears to belong to the broad family of lime-based mortars used across colonial architecture, but its behaviour raises a sharper question. Was it ordinary lime, or was it modified with local materials that made it more resistant to water? Scientific studies of historic lime mortars show that pure air lime hardens mainly by carbonation. Calcium hydroxide slowly reacts with carbon dioxide to form calcium carbonate. But lime mixed with pozzolanic materials such as crushed fired clay, volcanic ash, ceramic powder, or reactive siliceous particles can also harden through hydration reactions. A RILM review notes that Lima pozzolan mortars can be used for hydraulic structures and durable buildings in moist environments because they harden not only by carbonation but also by hydration. This matters because San Jose de Lules had exactly the ingredients that could have made such a hybrid mortar possible. The site is known to have included a brick kiln, and broken brick or fired clay powder is one of the classic materials capable of giving lime mortar more hydraulic behaviour. If the builders crushed kiln waste, failed bricks, ceramic fragments, or burnt clay into the mortar, they may have created a binder that could set harder, resist moisture better, and survive longer than simple limesand mortar. But this is where the mystery begins. The ruins do not come with a technical manual. No surviving recipe tells us the proportions of lime, sand, clay, crushed brick, organic additives, or water. We do not know the firing temperature of the lime, the type of limestone used, the grain size of the aggregate, or whether local indigenous builders contributed empirical knowledge about soils and binders. In other words, the wall still stands, but the formula that made it stand has disappeared. The water resistance may not have come from one ingredient alone. Historic mortars often perform well because of balance. Lime gives flexibility, sand controls shrinkage, crushed ceramic improves hydraulic setting, and pores allow moisture to evaporate instead of trapping it. Modern cement can be stronger, but in old brickwork it can also be too rigid and impermeable. Lime mortar survives differently. It accepts small movement, it breathes, it lets water enter and leave. That may be the secret behind San Jose de Lule. Not a waterproof wall, but a wall designed to manage water intelligently. The possibility of organic additives makes the puzzle even richer. Across many traditional building cultures, builders mixed lime with plant juices, fibers, animal products, cactus mucilage, sugars, oils, or ashes to adjust workability, water retention, and microstructure. San Jose de Lule was not just a church complex, it was an agricultural estate with sugarcane fields and workshops. Tourism and heritage records note that sugarcane was cultivated there in the Jesuit period, and some sources identify it as one of the early places where sugarcane was introduced or cultivated in Tucumán. That does not prove sugar-based additives were used in mortar, but it opens a scientifically plausible question. Did local agricultural byproducts enter the construction process? The brickwork adds another layer. Fired brick requires control of clay selection, drying, stacking, airflow, and kiln temperature. Common historical brick firing often falls in the range of roughly 700 to 900 degrees Celsius, depending on clay and kiln design. If San Jose de Lule produced consistent brick on site, the mission was not merely importing European building forms, it was operating a local materials laboratory. The kiln, the mortar, the clay, the lime, the drainage, and the wall thickness were all parts of one system. The foundations are just as important as the walls above them. Tucumán's wet season can move water through the soil, soften the ground, and attack the base of masonry. Yet the surviving walls suggest that the builders understood how to keep moisture from destroying the structure too quickly. They may have used compacted layers, rubble bedding, brick fragments, sloped surfaces, or hidden drainage paths. None of these methods would look spectacular on camera, but they are often the difference between a ruin that vanishes and a ruin that survives for centuries. The most overlooked mystery is therefore not a secret chamber or a buried treasure. It is the invisible design of moisture control. A building in this climate cannot survive by strength alone. It must breathe downward, outward, and upward. Rain has to be directed away. Groundwater has to be slowed. Wall pores mustn't remain saturated for too long. Salts must not crystallize with enough force to destroy the brick. If San Jose de Lule still preserves sections of old plaster and mortar, those fragments are not decoration. They are chemical evidence. There is also a cultural mystery hidden inside the engineering. Officially, this was a Jesuit mission, but missions were built by many hands: priest-craftsmen, indigenous labourers, local specialists, and people whose technical knowledge rarely entered written records. Argentina's heritage description says the Jesuits organised work, production, education, agriculture, and manual enterprises at San Jose del Monte de los Lules. That means the ruins may preserve a mixed technology, European religious planning fused with local materials, local climate knowledge, and indigenous practical skill. On a hilltop in Penafiel, northern Portugal, lies Castro de Monte Mozinho, a dead city of stone where an entire ancient settlement was planned across a mountain. The site was not discovered as a buried palace or a single spectacular tomb. Archaeological work began in the 20th century, with major campaigns from the 1930s, the 1970s, and later excavations that slowly revealed streets, walls, houses, monuments, tools, ceramics, coins, and traces of daily life. Castro de Monte Mozinho is often called the Dead City of Penafiel, but what survives there does not look like a dead place. It looks like a city whose logic is still visible. Built on the summit of Monte Mozinho, between the parishes of Oldros and Gallegos, the settlement covered more than 200,000 square metres, or over 20 hectares. It was protected by several defensive wall lines and occupied for a long period, from around the 1st century to after the 5th century AD, when the old Castro tradition and Roman urban culture overlapped in the same landscape. Sources describe its urban design as a mixture of indigenous courtyard houses with circular rooms and Roman influence shown in the regular layout of streets. The most disturbing question is not how these people built houses from stone, it is how they imposed order on a hill. Monte Mozinho was not flat ground. It was a raised, uneven summit, exposed to rain, wind, slope pressure, erosion and gravity. Yet parts of the settlement show a deliberate urban plan, streets aligned with one another, domestic blocks organised in repeated patterns, houses arranged around courtyards, and a central public space shaped by walls. In wider studies of Portuguese Castro culture, archaeologists note that orthogonal urban planning developed during the Romanization phase, when indigenous communities began absorbing Roman models of space, measurement, and administration. That explanation solves part of the mystery, but not all of it. Roman influence may explain the idea of order. It does not fully explain the execution. To draw a regular street system across an irregular hilltop, builders had to translate geometry into terrain. They had to know where one line should continue, where another should turn, how wide a passage should be, and how house fronts should align even when the ground beneath them changed height. A city plan on paper is simple. A city plan on a mountain is a technical problem. The remains suggest a society capable of controlling space with surprising precision. Monte Mozinho included circular Castro structures, rectangular Roman-style buildings, an ellipsoid upper enclosure, a probable temple with a rectangular cell and podium, funerary structures and streets connecting gates and sectors. The Biblioteca Virtual Miguel de Cervantes image catalogue identifies a road axis linking wall gates. Castro courtyard houses from the first half of the 1st century AD, ceramic kilns from the mid-1st century AD, a Roman monument podium from the last quarter of the 1st century AD, and a Roman house from the same period. This means the site was not created in one simple phase, it was layered. Older roundhouse traditions stood beside Roman rectangular architecture. Defensive walls followed the hill while internal spaces became more regular. The mystery is how the builders balanced two opposing systems, the natural shape of the mountain and the artificial geometry of a city. No ancient surveying instruments have been recovered that fully explain the process. There is no surviving map, no written construction manual, no marked measuring rods that tell us exactly how the builders controlled angles and distances. Yet the archaeology implies that some practical system existed. It may have been based on ropes, sight lines, measuring poles, repeated modules, and experienced builders who understood slope by eye. But even with simple tools, the achievement remains difficult. A small error in one street would multiply across a block. A mistaken level would send rainwater into a house. A poorly placed wall would collapse under its own weight. The terrain itself would have forced constant calculation. Builders had to cut into the hill, level domestic platforms, retain soil behind stone walls, and create usable surfaces without modern cement. Monte Mozinho's granite structures were assembled with local stone, and many walls depended on dry stone logic, weight, friction, interlocking surfaces, and the careful distribution of pressure. The strongest clue to their engineering skill is not one giant stone, but the survival of many ordinary walls after nearly 2,000 years of weathering. Water may be the hidden technology of the site. Northern Portugal receives significant rainfall, and a hilltop settlement of more than 20 hectares could not survive without controlling runoff. Every street, courtyard, and platform had to guide water away from foundations. The regular layout was therefore not only aesthetic or political, it was also hydraulic. Slight gradients, stone paving, gaps between blocks, and the orientation of streets could all turn rain from a destructive force into a manageable system. If that control failed, erosion would have erased large parts of the settlement long before modern archaeologists arrived. Monte Mozinho also raises a logistical problem. A settlement of this scale needed labour, planning, food, timber, stone, metal tools, and social authority. Excavations have recovered Iron Age and Roman ceramics, glass, roof tiles such as tegulae and imbrices, millstones, coins, metal objects, agricultural tools, defensive items, jewellery, bronze and silver ornaments, granite statuary, altars, and epigraphic fragments. These finds suggest a community connected to farming, craft production, trade, religion, and Roman administrative culture, not an isolated tribal village. The shift from circular houses to rectangular Roman forms is especially important. Circular buildings are usually harder to integrate into strict grids, while rectangular structures naturally support orthogonal planning. At Monte Mozinho, both forms existed together. This creates one of the most fascinating archaeological tensions at the site. Was the regular plan imposed by Roman models, or did local builders already possess a strong tradition of spatial organisation before Rome transformed it? Studies of Portuguese castros show that these communities had long occupied strategic hilltops overlooking river basins, agricultural land, mineral resources, and transport routes. Their settlements were not random shelters, they were chosen for control. The defensive system deepens the puzzle. Monte Mozinho was enclosed by multiple wall lines, with sources describing 3 or 4 circuits, depending on the surveyed sector and interpretation. The walls did more than protect the population. They divided the mountain into controlled zones. Gates, ramps, and corridors shaped movement. Attackers could not simply rush into the city. They had to pass through narrowed approaches and changing elevations. In that sense, the settlement was both an urban organism and a defensive machine. The probable temple and Roman monument add another layer. A city that contains domestic quarters, production areas, funerary spaces, defensive walls, and monumental architecture is a place where power had become visible. Planning was no longer just about survival. It was about hierarchy. Streets told people where to move. Walls told them where boundaries lay. Monuments told them who or what mattered. This is why Monte Mozinho is so valuable. It captures the moment when an indigenous hill-fort world was being reorganized into a Romanized urban landscape. In Bacarra, Ilocos Norte, northern Philippines, a small museum beside an old church hides a larger question. How much of the ancient maritime world passed through these shores before history was written down? Museo de Bacarra is not a ruined temple or a buried city. It is a local heritage museum built from objects preserved by families, church records, religious items, antique furniture, agricultural tools, and cultural artifacts connected to the town's memory. Reports describe it as a museum of Spanish-era relics, local objects, and community-contributed collections, including church archives connected to Bacarra's colonial past. But the deeper story begins when these local objects are placed against the wider archaeology of the Philippines, a country where imported ceramics, maritime trade goods, and seafaring traditions point to a world far older than the Spanish arrival. The museum's discovery story is simple. Around the early 21st century, Bacarra gathered objects from local families and preserved them in a museum near the church complex. One travel account notes that about 1 year was spent collecting artifacts and remnants donated by residents, later organized into sections about livelihood, agriculture, history, politics, culture, religion, and everyday life. At first glance, Museo de Bacarra looks like a quiet provincial museum. But its real value is not only what sits inside the display cases, it is what those objects suggest about a northern Philippine coast that was never isolated. The National Museum of the Philippines records that imported stoneware and porcelain found across the country came from China, Vietnam, Thailand, and Europe, dating from the late Tang period, 618 to 906 CE through the 18th century. These ceramics were not decorative accidents. They were part of long-distance maritime trade, prestige exchange, and social ranking in pre-colonial and colonial Philippine communities. This is where Bacarra becomes more interesting. Ilocos Norte faces the South China Sea, a maritime corridor shaped by monsoon winds, currents, coastal settlements, and exchange routes. If trade ceramics and foreign objects reached Philippine communities for centuries, the question becomes unavoidable. What kind of seafaring technology made this possible before European ships dominated the region? The most important unsolved layer is Austronesian shipbuilding. The Philippines sits inside the world of Austronesian-speaking peoples, whose expansion from Taiwan into the Philippines and farther across island Southeast Asia and the Pacific is one of the greatest maritime movements in human history. UCLA's Fowler Museum describes Proto-Austronesian peoples as evidenced in Taiwan around 5,000 years ago, with seafaring agriculturalists spreading through the Philippines and Indonesia by about 3,300 years ago, then moving eastward into the Pacific as far as the Solomon Islands and the Marianas. Yet the boats that carried this expansion remain partly invisible. Archaeologists know key principles: outriggers for stability, sewn plank or lashed construction, flexible hulls, and wooden joints that could survive waves without relying on heavy iron nails. In the Philippines, the best-known evidence comes not from Bacarra but from Butuan, where ancient barangay boats revealed a sophisticated lashed lug tradition. These vessels show that Philippine boat builders could join planks edge to edge, fasten them with wooden dowels, and tie internal lugs with fibre lashings, creating a hull strong enough for riverine and coastal movement and possibly wider regional trade. The gap is the mystery. If northern Luzon communities received foreign ceramics and participated in maritime exchange, where are their ships? Where are the shipyards, repair areas, anchors, timber working tools, rope remains, and harbour structures? Organic materials decay quickly in tropical environments, and coastal zones are easily destroyed by storms, erosion, construction, and changing shorelines. The result is a strange imbalance. Trade goods survive in houses, graves, museums, and disturbed sites, but the vessels that moved them often vanish. Bacarra stands inside that silence. This is not a fantasy of lost technology, it is a genuine archaeological problem. The National Museum notes that Philippine tradeware collections include whole vessels and fragments recovered through excavation, donation, purchase and confiscation beginning in the 1950s, with important assemblages from places such as Calatagan, Santa Ana, Porac, Oton and Cebu. The ceramics prove movement, but the transport system behind that movement is harder to reconstruct. The engineering question becomes sharper when we consider distance. A ceramic bowl made in China or Vietnam did not simply appear in northern Luzon. It passed through production centres, merchants, ports, seasonal winds, cargo handling, coastal redistribution, and finally local possession. Some routes may have used Chinese junks, some Southeast Asian traders, and some local Austronesian vessels. But how much of the final transport was handled by local Philippine sailors? How far could their boats travel? How much cargo could they carry? Could smaller coastal craft connect with larger ocean-going ships offshore? These are still difficult to answer with precision. The technology of navigation is equally elusive. Austronesian sailors across the Pacific are famous for reading stars, swells, winds, birds, clouds, and currents. But in the northern Philippines, the material evidence for how this knowledge was taught, stored, and transmitted is almost absent. No ancient navigation manuals survive from Bacarra. No carved star charts have been found there. No shipwright's workshop has been excavated beneath the town. The knowledge may have lived in memory, apprenticeship, and repeated seasonal practice rather than in written records. The ceramics raise another technical question: value recognition. Imported porcelain and stoneware were high-fired materials, often produced at temperatures far beyond ordinary low-fired earthenware. Chinese and Southeast Asian kilns could produce durable vitrified wares that survived centuries underground or underwater. In Philippine communities, these objects became markers of prestige, ritual value, and exchange power. But how did local people classify them? Were they judged by colour, sound, weight, translucency, glaze, or origin? A recent paper on Oriental tradeware ceramics in Philippine archaeological sites argues that identification practices still need improvement because many classifications depend heavily on authority and require better documentation and cross-referencing. This matters because every misidentified ceramic changes the map of trade. A fragment labelled Chinese might actually be Vietnamese. A jar thought to be late medieval might belong to a later colonial exchange. A household heirloom may have moved through generations before entering a museum. In a place like Museo de Bacarra, where many objects are community preserved rather than recovered from controlled excavation, the mystery is not only what the artifacts are, but where they originally came from, how long they circulated, and what social meaning they carried before being displayed. There is also the problem of missing context. Archaeology depends on layers, soil depth, associated objects, burial position, charcoal, shell, bone, hearths, and architecture. Once an object is removed from its original setting, much of its scientific value is weakened. Museo de Bacarra preserves memory. But not every artifact can answer archaeological questions with the same precision as a controlled excavation. This creates a documentary tension. The museum protects the surviving objects while also reminding us of how much information may already be lost. What do you think happened to the ships that once connected these ancient trade routes? Share your thoughts in the comments below. I'd love to hear your theory. Nestled in the limestone hills of Rabacal, near Penela in central Portugal, a late Roman villa conceals one of the most intriguing engineering questions of Lusitania. How did a rural estate preserve such delicate mosaic floors for roughly 16 centuries? The Villa Romana de Rabacal began to emerge through archaeological campaigns carried out from the early 1980s onward. Excavations revealed a residential sector, a bath complex, agricultural courtyards, storerooms, workshops, and some of the most distinctive late Roman mosaics found in Portugal. The villa is generally dated to the 4th century AD and is often interpreted as the country residence of a wealthy family connected with nearby Coimbriga, one of the most important Roman cities in the region. At first glance, Rabacal looks like another elegant Roman villa. Rooms arranged around open spaces, walls reduced to foundations, floors broken by time. But the deeper mystery is not in what collapsed, it is in what survived. Mosaic floors are fragile systems. They're not simply decorations laid on soil. They're engineered surfaces made from thousands of small stone cubes, each one depending on the stability of the layers beneath it. If the ground moves, if water rises, if mortar shrinks, if heat expands one layer faster than another, the image fractures. Yet, at Rabacal, large sections of the mosaic pavement remained readable after more than 1,500 years. The mosaics themselves are unusually ambitious for a rural villa. Sources describe figurative scenes including the seasons, a quadriga, and a seated female figure, alongside geometric and vegetal compositions considered highly distinctive in their design. The question is not only who paid for such work, but how the craftsmen controlled it. Roman mosaics could involve tesserae only a few millimeters to a little over 1 centimeter wide. Across a large room, even a tiny cumulative error would distort circles, stars, borders, and interlocking geometry. At Rabacal, the visual order suggests that the workers were not improvising. They were following grids, axes, center points, and proportional systems that have left almost no physical trace. This is where the villa becomes more than a decorative monument. It becomes evidence of an invisible technical culture. No complete drawing board has survived. No manual from the workshop was found beside the floor. Yet the geometry implies planning before placement. The builders had to establish the room dimensions, prepare the foundation, mark reference lines, and then place thousands of tesserae while keeping the surface flat enough for walking and precise enough for visual symmetry. The mystery is not supernatural, it is practical, a lost construction discipline transmitted by trained hands rather than written theory. The most important secret may lie under the visible surface. Roman mosaic floors were normally built as stratified systems. A technical study of Roman mosaic construction describes the classic sequence from Vitruvian tradition: statumen, a preparatory layer of large stones; rudus, a gravel and mortar layer used for levelling; nucleus, an impermeable lime and powdered pottery mortar layer protecting the pavement from ground moisture; and finally, the bedding layer holding the tesserae. This was not decoration resting on dirt. It was a miniature civil engineering platform. That layered structure matters because cracking is rarely caused by the top surface alone. Cracks begin when stress moves upward. Soil settles, moisture swells, lime mortar shrinks as it cures. Seasonal temperature changes expand and contract materials at different rates. A single rigid slab can split under these forces, but a well-designed layered floor can behave differently. Coarser lower layers distribute weight. Gravel and stone reduce direct soil movement. Lime mortar creates bonding. Crushed ceramic material can improve resistance to humidity. Finer upper layers receive the mosaic without forcing the tesserae to absorb all the stress. This is why the Rabacal floors are so important for a documentary angle. The apparent miracle is not that Roman artisans made a beautiful picture. It is that they created a foundation capable of protecting that picture for centuries. Modern conservation science shows that Roman mortars and plasters often used lime mixed with pozzolanic or ceramic aggregates such as crushed brick, tile or pottery. These ingredients could improve hydraulic behavior, adhesion, durability and moisture resistance. Studies of Roman mortars from other sites show multi-layer technologies using lime mortars, pozzolanic lightweight aggregates, and coccio pesto, while broader research describes Roman pozzolanic mortars as highly optimized and durable pre-industrial materials. For Rabacal, the unresolved question is how much of this was calculated and how much was inherited craft knowledge. The builders did not possess modern cement chemistry, laser levels, or structural simulation software. Yet they understood that a pavement needed drainage, compaction, graded materials, and compatible layers. They knew the surface could not be isolated from the ground below. They seemed to have understood that beauty depended on invisible engineering. The crack-resistant foundation becomes even more mysterious when we consider the villa's environment. Central Portugal experiences seasonal shifts in temperature and humidity. A rural estate also carried practical loads: footsteps, furniture, water movement, repairs, abandonment, burial, and later exposure through excavation. A mosaic floor surviving in such conditions must have resisted not one disaster but thousands of small stresses over time. Each year brought expansion, contraction, moisture, drying, root pressure, and soil movement. The fact that the floor did not simply disintegrate suggests that the ancient builders created a stress management system, not just a decorative floor. There is also a hydraulic dimension. Rabacal included a bathhouse and spaces linked to water use. Excavations identified residential areas, agricultural courtyards, warehouses, workshops, and bathing facilities, meaning the villa was not a static mansion but a working estate with controlled water, heat, and service zones. Roman baths required drainage, waterproofing, heated rooms, and carefully managed surfaces. Even if not every mosaic belonged to a wet room, the entire complex belonged to a culture that understood moisture as an engineering threat. A cracked floor was not only ugly, it allowed water to enter, weaken mortar, and accelerate collapse. The strangest part is that Rabacal was not Rome, Ravenna, or Constantinople. It was a rural villa in Lusitania. Yet its design language and technical execution suggest access to elite artisans and long-distance artistic ideas. The World Monuments Fund notes that the villa's architecture, bas-reliefs, and mosaics are unique, with figurative designs that differ substantially from other unknown examples. That uniqueness raises a deeper question. Was Rabacal an isolated luxury residence, or evidence that late Roman rural estates in Portugal are more technically sophisticated than the surviving historical record suggests? The engineering mystery is sharpened by the absence of the workshop itself. We can see the finished pavement, but not the full process. Where were the tesserae cut? How were colours selected? How were geometric patterns transferred from concept to floor? How many craftsmen worked at once? Did they use cords dipped in pigment, wooden templates, proportional compasses, or modular grids? Archaeology can identify materials and layouts, but the choreography of labour has mostly vanished. The foundation tells the same story. We can describe the likely Roman system: compacted ground, stone layers, mortar layers, ceramic-rich waterproof layers, bedding mortar, tesserae. but the exact recipe remains harder to recover. Ancient builders adjusted mixtures according to local stone, lime quality, sand grain size, ceramic fragments and water availability. A small change in lime burning temperature or aggregate ratio could alter curing, shrinkage and long-term strength. This means Rabacal may preserve not a single formula, but a local adaptation of Roman engineering knowledge. On a 40-metre promontory above the Mediterranean Sea behind Sa Caleta in Lloret de Mar, Catalonia, the ruins of Turo Rodo look small, but they hide one of the most revealing engineering puzzles of the Iberian world. Turo Rodo was identified and excavated as part of the archaeological heritage of Lloret de Mar. Today it belongs to the Musea Obert de Lloret route, and one of its houses has been experimentally reconstructed using evidence from the excavation itself. Local stone, mud, lime, wood, reed, straw and building techniques considered typical of the Iberian period. At first glance, Turo Rodo does not look like a monument built to impress kings. It is not a palace, not a temple, not a city of giant stones. It is a compact Iberian settlement placed on a small peninsular headland about 40 metres above sea level, with cliffs on the eastern and southern sides, Sa Caleta Beach to the west, and a narrow land connection to the north. But this is exactly what makes the site mysterious. Its builders were not trying to dominate the landscape with size, they were trying to use the landscape as a machine. The promontory itself was the first layer of engineering. The settlement was placed where the sea, the cliff, and the isthmus created a natural defensive triangle. The eastern and southern faces needed little artificial protection because the cliffs already acted as walls. The northern approach, only about 50 metres wide, was the vulnerable point. This means the ancient builders understood that the cheapest wall is the one nature has already built. Long before modern military topography, they selected a site where defence, visibility, maritime access, and restricted movement were all concentrated in one small space. This raises the first unanswered question. How did a small Iberian community evaluate the landscape so precisely? Today, archaeologists can use GIS, viewshed analysis, contour maps, and digital terrain models to calculate visibility and defensive exposure. At Turo Rodo, the ancient solution was achieved without surviving plans, written measurements, or surveying instruments. The inhabitants seem to have understood wind, slope, sea access, and enemy movement through lived experience. The site was not randomly placed on high ground. It was positioned where a watcher could read the coast, where small boats could use Sa Caleta below, and where an attack from land would be forced into a narrow approach. The second technical mystery is the settlement plan. Turo Rodo was small, but not chaotic. The houses were organised around a central open space, with domestic units attached to the defensive perimeter. This type of planning turns architecture into defence. A wall is not only a barrier, a house can become part of the barrier, a street can become a controlled corridor, a courtyard can become a shared work area, gathering point or emergency space. The logic is simple, but the execution is not. To make it work, the builders had to coordinate the position of rooms, entrances, wall thickness, drainage, roof loads, and circulation inside a settlement with almost no wasted area. The most important mystery, however, is not the stone, it is the mud. The reconstructed Iberian house at Turo Rodo is classified as mud architecture. According to the official heritage description, the basic system used a stone base to insulate the structure from damp, sun-dried brick walls and a roof made from mud mixed with plant materials over a reed frame. This sounds primitive only if we misunderstand the material. Mud architecture is not just wet earth piled into a wall. It is an engineered composite system. Earth provides mass. Clay provides binding. Sand or silt controls shrinkage. Straw, reed, or other fibers reduce cracking and improve tensile behavior. Stone lifts the vulnerable earthen wall above ground moisture. The roof must be light enough not to crush the walls, but thick enough to resist rain, sun, and coastal wind. That balance is the hidden technology of Turo Rodo. If the clay content is too high, the wall shrinks and cracks as it dries. If the clay content is too low, the brick loses cohesion. If the plant fibers are too long, the mixture becomes weak and uneven. If they are too short, they fail to bridge cracks. If the brick dries too quickly under the Mediterranean sun, it can warp. If it dries too slowly, it can deform or decay. Every stage depends on decisions that rarely leave direct archaeological traces. Where the earth was taken from, how it was sieved, how much water was added, how long the mixture rested, how the bricks were shaped, how long they dried, and how damaged blocks were repaired. This is why Turo Rodo is valuable as an ancient engineering mystery. We can see the result, and experimental reconstruction can imitate the method, but the exact recipe used by the original builders is still difficult to recover. The official reconstruction used typical Iberian period materials and techniques, but a reconstruction is not the same as recovering the full operational chain. The ancient builders probably did not follow a written formula. Their knowledge was stored in hands, habits, seasons, and local memory. A builder knew when earth felt right. A roof maker knew how much reed could carry wet mud. A repairer knew which cracks were dangerous and which were harmless. Archaeology can document materials, but it cannot fully recover touch. The roof is even more mysterious than the walls. A mud and plant roof placed over reeds sounds simple, but structurally it is a dangerous system if miscalculated. Wet mud is heavy, reeds bend, wooden beams move with humidity. Coastal wind creates uplift. Rain adds temporary weight. Salt air attacks organic materials. For the roof to survive, the builders needed to control load distribution across the reed frame and walls. The mud layer had to be thick enough to seal the surface, but not so thick that it collapsed the structure. The slope had to remove water, but a steep roof would require different framing. A nearly flat roof would need maintenance and careful surface compaction. These are not decorative choices, they're engineering decisions. The stone base was another quiet invention. The official description says the stone base insulated the house from damp. That one detail reveals a sophisticated understanding of material failure. Mud brick can be strong in compression, but it is vulnerable to rising moisture. If water enters the base of the wall repeatedly, salts crystallize, clay bonds weaken, and the wall begins to crumble from below. By raising the earthen walls on stone, the builders separated the most fragile material from the wettest zone. They were not only building walls, they were designing a moisture barrier. This technique connects Turo Rodo to a much wider Iberian tradition. Recent studies of earthen architecture on the Iberian Peninsula show that mud brick and other earthen techniques were important, but unevenly distributed in Iron Age contexts, and that mud brick has often been linked to Eastern Mediterranean and Levantine building traditions that spread through Phoenician and other contacts between roughly the 8th and 6th centuries BC. Other research stresses that earthen architecture in Iberia has been understudied, partly because these materials decay, fragment, and are often harder to interpret than stone. This makes Turo Rodo important because it preserves not just the outline of a house, but a rare chance to reconstruct how an Iberian building may have actually worked. And still, the mystery remains. Was this technology imported, adapted, or invented locally? The Mediterranean coast of Catalonia was not isolated. Iberian communities interacted with wider trade networks, and coastal settlements could receive goods, ideas, tools, and building habits from many directions. Mud brick traditions may have moved through contact with Phoenician, Greek, or other Mediterranean builders. But the final form at Turo Rodo was not copied blindly. It was adjusted to a specific cliff, a specific climate, a specific settlement plan, and specific local materials. This is where the mystery becomes more subtle. The technique may have foreign roots, but the engineering solution was local. Inside the reconstructed house, the domestic objects, a loom, stools, baskets, millstones, and a hearth, show that architecture was tied to everyday production, not just shelter. A house had to hold people, tools, smoke, food processing, weaving, storage, and heat. The walls had to resist not only weather but daily use. A hearth changes humidity and temperature. Grinding stones create dust and vibration. Stored grain attracts pests. A loom needs stable floor space. Every small object reveals pressure on the building. The house was a workshop, kitchen, storage unit, and living space compressed into one technical environment. Near San Pedro de Alcántara in Marbella, Spain, a ruined Roman bathhouse still carries a name that sounds like a warning: Las Bóvedas, the vaults. The site was recognized as Roman in the early 20th century, though local memory had noticed the strange domed ruins long before. Today, archaeology places the complex around the 2nd or 3rd century AD, when this coast belonged to Roman Baetica, one of the richest provinces of the Western Empire. The ruins stand near the Guadalmina River, close to the sea, and near other Roman remains linked to fish salting activity and coastal settlement. At first glance, Las Bóvedas looks small compared with the great imperial baths of Rome, but that is exactly what makes it more mysterious. This was not a palace of emperors, it was a provincial thermal building, and yet its surviving structure shows a level of technical knowledge that still raises difficult questions. How did Roman builders create a vaulted concrete complex that could survive nearly 1,800 years of weather, abandonment, coastal humidity, earthquakes, and human damage? The most important clue is hidden in the name itself. Las Bóvedas is remembered for its vaults. The complex is described as a small but monumental Roman bathhouse, with rooms arranged around a central octagonal space, and several sources describe 7 vaulted stone rooms, probably dating to the 2nd or 3rd century AD. The central geometry is not random. An octagonal plan gives the building both symmetry and structural balance. It allows rooms to radiate around a controlled core, while the vaulted ceilings push their weight downward and outward in predictable directions. In modern engineering, this would be studied through stress diagrams, compression paths, and material modeling. Roman builders did it with geometry, tools, experience, and a construction tradition passed from hand to hand. The ancient mystery is not that the Romans used concrete. The mystery is how well they understood what concrete could become. Roman concrete, known as opus cementitium, was not poured like modern reinforced concrete. It was a mixture of lime, aggregate, stone, brick fragments, sand, and sometimes pozzolanic material. In many Roman buildings, the result was not simply a wall filler, but a structural mass capable of forming vaults, domes, cisterns, aqueducts, and harbour works. Las Bóvedas belongs to that same world, a structure where curved masonry and concrete were used to create space, strength, and environmental control at the same time. The survival of the vaults is especially striking because concrete normally suffers under repeated stress. Coastal air brings salt, rain brings moisture, thermal baths bring steam, heat, and condensation. Over centuries, these forces can open cracks, weaken mortar, and dissolve binding materials. Yet parts of Las Bóvedas still preserve their vaulted form. The answer may lie in a Roman material science that modern researchers are only beginning to reconstruct. A major study in Science Advances reported that ancient Roman concrete often contains limeclasts, once dismissed as poor mixing, but now understood as possibly linked to hot mixing and long-term self-healing behavior. When water enters small cracks, these calcium-rich particles can react and recrystallize, helping seal damage over time. This does not mean we know the exact recipe used at Las Bovedas. That is where the mystery becomes serious. The famous volcanic pozzolana of central Italy was not always available in distant provinces. Builders in Baetica had to adapt. They may have used local sands, crushed ceramic, lime, coastal stone, and recycled brick to imitate the chemical behavior of more famous Roman concrete. If so, Las Bovedas was not just a copy of Roman technology, it was a local engineering solution. The unanswered question is whether its builders followed a formal imperial recipe or whether they adjusted the mix by practical testing, watching how mortar cured, how it cracked, how it resisted steam, and how it behaved inside a heated bathhouse. The vaults also raise a question of construction method. Before concrete hardened, it needed support. Roman builders probably used wooden centering, temporary frames shaped to the curve of the vault, but wood leaves little trace after nearly 2 millennia. We see the surviving shell, not the lost choreography of labour. How many workers built each vault? How long did the concrete cure before the supports were removed? Did they build each room separately, or did the whole structure behave as one connected mass? The archaeology preserves the answer only indirectly, in the way the walls meet, the way the loads descend, and the way the octagonal core holds the building together. A bathhouse was never only a building. It was a machine for heat, water, air, and human movement. Roman baths commonly used the hypercore system, a form of underfloor heating in which hot air circulated beneath raised floors supported by small brick pillars called pillae. The hot air could then travel upward through hollow wall tiles, known as tubuli, before escaping through vents. This system is often described as ancient central heating, but that phrase can make it sound simpler than it was. In reality, a hypocaust required careful control of fire, airflow, pressure, room sequence, wall thickness, floor height, and fuel consumption. At Las Bovedas, the technical question is how such a small complex managed thermal zoning. A Roman bath needed different temperatures, cold spaces, warm transition rooms, and hotter rooms for sweating and bathing. The building had to move people through a controlled climate. It had to keep hot areas hot, prevent warm rooms from losing heat too quickly, and stop steam from destroying the walls. In a modern spa, engineers use pumps, thermostats, insulation panels, fans, sensors, and mechanical ventilation. Roman builders relied on architecture itself. The shape of the rooms, the height of the vaults, the voids beneath the floor, and the channels inside the walls all became part of the machine. The domed and vaulted ceilings may have helped with this environmental control. Curved ceilings can collect and redirect warm air. They can reduce sharp corners where condensation gathers. They can distribute pressure and heat more evenly than flat timber roofs. In a humid bathhouse, this mattered. A flat wooden ceiling above steam would decay. A stone or concrete vault could survive heat and moisture better, especially if the mortar was dense and the surface was properly finished. This may explain why the most visible mystery of Las Bovedas, the vaults, is inseparable from the hidden mystery of the heating system. Water introduces another layer. Roman thermal buildings required a constant supply of clean water and an equally reliable way to remove wastewater. Las Bovedas stands near the mouth of the Guadalmina River and close to the coast, but the exact ancient water management system is not fully visible today. The building must have needed basins, drains, gradients, and possibly storage features. Nearby fish salting pools show that this coastal zone was already shaped by Roman hydraulic and industrial activity. The unresolved problem is how the bathhouse maintained enough water pressure and drainage efficiency without the full infrastructure now surviving above ground. This is where Las Bovedas becomes more than a ruin. It becomes evidence of a lost technical culture. The Romans did not separate architecture from physics. A wall carried weight, but it also stored heat. A vault covered a room, but it also controlled moisture. A floor supported people, but it also hid moving air. A drain removed water, but it also protected the foundation. Every part of the bathhouse had more than one function. The location adds another uncertainty. Some traditions connect the baths with the Roman settlement known as Kilniana or Silniana, whose exact position remains debated. If Las Bovedas belonged to a lost coastal settlement, then the bathhouse may be one of the few surviving fragments of a much larger urban or semi-urban system. The missing streets, houses, workshops, aqueduct lines, and service buildings make the ruins feel incomplete. We are looking at the surviving engine room of a community whose full map has partly disappeared. Hadrienopoulos lies hidden among the forested hills of Paphlagonia, in today's Eskipaza district of Karabuk province, northern Turkey. For centuries, the city disappeared beneath farmland and dense vegetation until systematic archaeological excavations began in *2003**, revealing the remains of a surprisingly sophisticated Roman and Byzantine settlement. More than **, 14 public buildings *** have since been identified, including churches, baths, defensive structures, villas, ceremonial buildings, and remarkably well-preserved mosaics. Yet the greatest mystery of Hadrienopoulos is not what archaeologists uncovered. It is how such an advanced urban centre emerged in what was once considered a remote frontier of the Roman world. Excavations quickly challenged long-standing assumptions about the region. Archaeological evidence indicates that occupation at the site stretches back far beyond the Roman Empire. Material recovered from different layers includes remains dating to the late Chalcolithic period, roughly 4,500 to 3,500 BC continuing through the Bronze Age, Iron Age, Roman and Byzantine periods. This means the same landscape supported human activity for nearly 6,000 years with successive civilizations repeatedly rebuilding upon earlier foundations. Yet despite decades of excavation, researchers still cannot fully explain why this particular location became such a long-lived center of settlement. The surrounding landscape offers neither an extensive river system nor fertile plains comparable to the great Roman cities farther west, raising fundamental questions about its economic and strategic significance. Perhaps the first engineering mystery appears before entering any building. Hadrienopoulos occupies uneven limestone hills rather than a broad valley floor, forcing ancient builders to create stable construction platforms across highly irregular terrain. Modern surveys reveal that many structures were not simply placed on natural ground, but rested upon carefully prepared terraces, retaining walls, and artificial levelling systems. Constructing an entire urban centre under such conditions would have required moving enormous quantities of rock and soil without modern excavation equipment. Archaeologists can observe the finished terraces, but still cannot reconstruct the precise sequence of surveying, cutting, filling, and stabilization that allowed Roman engineers to transform the rugged landscape into a functioning city. Unlike famous imperial capitals where construction records occasionally survive, Hadrienopoulos offers almost no written evidence describing how these massive earthworks were organized. The city becomes even more puzzling when its mosaics are examined. Excavations have uncovered some of the finest floor mosaics ever discovered in northern Anatolia, preserved inside churches, villas, and ceremonial buildings. Many contain remarkably detailed images of horses, deer, lions, peacocks, griffins, vines, and geometric compositions produced from thousands of tiny tesserae. Individual stone cubes often measure only ***, 5 to 8 millimeters ***, demanding extraordinary precision during installation. Specialists have noted stylistic similarities with workshops from major artistic centres such as Antioch and Zeugma, yet Hadrienopoulos itself lay hundreds of kilometres away from these famous mosaic traditions. No workshop producing tesserae has yet been discovered within the city, nor have archaeologists identified where the artisans lived, where they obtained their pigments, or whether the craftsmen travelled from distant provinces. The finished floors demonstrate exceptional technical ability, but the production system behind them has almost completely vanished. The raw materials themselves introduce another unresolved question. Every mosaic required carefully selected limestone, marble, coloured stone, and occasionally glass tesserae. Public buildings demanded enormous quantities of cut blocks, fired bricks, lime mortar, timber beams, roof tiles, and decorative stone. Yet no large quarry or industrial production centre has been securely identified close enough to explain this level of construction. Transporting heavy building materials across mountainous terrain would have required organised logistics, road maintenance, animal power, and substantial labour. Roman engineering manuals describe transport techniques elsewhere, but Hadrienopoulos has preserved almost none of the infrastructure that supplied its ambitious building program. Whether most materials were produced locally or imported through regional trade networks remains uncertain. Water management creates another technical puzzle. Roman cities typically depended upon monumental aqueducts that remain visible today, but Hadrienopoulos presents a very different picture. Archaeologists have identified cisterns, drainage channels, reservoirs, and hydraulic installations associated with bath complexes and domestic buildings. However, no massive aqueduct supplying the settlement has yet been documented. This has led researchers to suggest that the city may have relied upon springs emerging from the surrounding hills, underground water collection systems, or a network of smaller conduits now destroyed by erosion and later agriculture. If so, Roman engineers were adapting standard hydraulic principles to an environment where monumental aqueduct construction may not have been practical. Exactly how sufficient water reached public baths, churches, workshops, and households throughout the year remains one of the site's most significant unanswered engineering questions. The Roman baths themselves deepen the mystery. Bathhouses were among the most technologically demanding buildings of the ancient world, consuming vast quantities of water, fuel, and construction materials. Excavations at Hadrienopoulos have revealed evidence for **** hypercoursed heating ****. The sophisticated Roman system in which hot air circulated beneath raised floors, supported by small brick pillars before rising through hollow wall flues. Maintaining such a system required careful temperature regulation, continuous wood supplies, skilled furnace operators, and durable ceramic construction capable of surviving repeated heating cycles. Establishing this level of engineering in an isolated upland settlement suggests the presence of highly trained builders and technicians. Yet no inscriptions identify the engineers responsible, no workshops manufacturing hypercourse components have been found, and no documents explain how such expertise reached this frontier region. Equally intriguing is the concentration of religious architecture. Archaeologists have uncovered several churches decorated with elaborate mosaics and symbolic imagery, leading some Turkish researchers to describe Hadrienopoulos as the **** zeugma of the Black Sea ***, because of the artistic richness preserved beneath its soil. Constructing multiple basilicas demanded skilled stonemasons, carpenters, mosaic artists, plaster specialists, and reliable financial support over many decades. Such investment implies a prosperous community with access to substantial economic resources, yet historical sources mention the city only briefly. The apparent mismatch between its archaeological richness and its limited historical visibility remains difficult to reconcile. Animal imagery found throughout the mosaics introduces another subtle mystery concerning knowledge transfer across the Roman Empire. Alongside native wildlife appear representations of creatures such as peacocks and exotic animals that local craftsmen were unlikely to have observed directly. These images demonstrate access to artistic models, illustrated manuscripts, imported objects, or itinerant craftsmen carrying visual traditions across enormous distances. The mosaics therefore preserve not only artistic achievement, but evidence for invisible communication networks through which technical knowledge, iconography, and construction practices circulated across the Mediterranean. The routes by which these ideas reached Hadrienopoulos are still poorly understood. Long before Portugal existed as a nation, before Roman legions crossed the Iberian Peninsula, and before medieval castles crowned the mountains, an Iron Age community constructed a fortified settlement on a granite hill overlooking the Ave Valley in northern Portugal. Today, known as Castro de Monte Padrao, the ruins appear modest. Broken stone walls scattered across a wooded summit near Santo Tirso, roughly 25 kilometers northeast of Porto. Yet beneath those weathered stones lies a remarkable engineering puzzle. Archaeological excavations have revealed multiple defensive walls, carefully planned circular dwellings, Roman period occupation, and centuries of continuous use. But despite decades of research, archaeologists still cannot fully explain how a relatively small Iron Age society mastered the surveying, quarrying, transportation, and construction techniques required to build and maintain such a strategically engineered hill fort. The site first attracted archaeological attention during the 20th century, with systematic excavations beginning in the 1980s and continuing through several research campaigns. Excavations uncovered defensive ramparts, domestic structures, pottery, iron tools, bronze ornaments, Roman ceramics, coins, and evidence that the settlement remained occupied from approximately the 4th or 3rd century BC into the Roman imperial period. This long occupation is itself significant. Instead of abandoning the hill fort after Rome arrived, its inhabitants adapted it, creating a rare opportunity to study how indigenous engineering traditions interacted with Roman technology. The first mystery begins with the choice of location. Monte Padrao rises only about 300 meters above sea level, far lower than many neighboring mountains. At first glance, it seems an ordinary hill, yet its summit commands an exceptional panoramic view over the Ave River basin, one of the most important natural corridors linking Portugal's Atlantic coast with the interior of the Iberian Peninsula. From this position, movement through the valley could be observed for many kilometers. Even more importantly, the surrounding slopes are naturally steep, reducing the amount of artificial fortification required to defend the settlement. Modern geographic information systems demonstrate that hill fort placement throughout northwestern Iberia often maximized visibility while minimizing construction effort. Such optimization raises an intriguing question. Did Iron Age builders simply rely on generations of practical experience? Or had they developed an empirical method of terrain analysis that functioned much like primitive military surveying? Without maps, aerial views, or optical instruments, They consistently selected locations offering the greatest defensive advantage. The knowledge behind those decisions has disappeared. The defensive walls themselves deepen the mystery. Monte Padrao belongs to the Castro culture, famous for constructing massive granite fortifications throughout northern Portugal and Galicia. Granite is an exceptionally durable igneous rock, with a compressive strength commonly exceeding 150 megapascals and a Mohs hardness of approximately 6 to 7. Even with modern steel tools, granite demands considerable effort to shape. Yet the builders of Monte Padrao extracted hundreds, perhaps thousands of granite blocks, transported them uphill, and assembled them into walls that have survived more than 2,000 years. Many surviving sections display remarkably tight stone fitting despite the apparent absence of mortar. Instead of relying on binding materials, the builders exploited the geometry of each stone. Larger blocks formed stable foundations, while progressively smaller stones filled gaps, distributing stress throughout the structure. Modern dry stone engineering demonstrates that such walls remain flexible under seasonal expansion, heavy rainfall, and minor ground movement because the individual stones can adjust microscopically without catastrophic failure. What remains uncertain is how Iron Age masons consistently achieve this precision. Archaeologists propose the use of iron chisels, hammerstones, wooden wedges, and fire-setting techniques in which heated granite was rapidly cooled to create controlled fractures. Experimental archaeology confirms that these methods work individually, but no experiment has yet reproduced the construction of an entire Castro fortification on the original scale. Equally mysterious is the transportation problem. Granite blocks weighing several hundred kilograms had to be moved from nearby outcrops to the summit. There is no evidence for wheeled cranes, draft animals capable of lifting such loads uphill, or sophisticated mechanical devices. The accepted explanation involves wooden rollers, sledges, rope made from plant fibers, and coordinated human labor. Yet even these methods demand careful organization. Calculations based on experimental reconstructions suggest that moving a single 1-ton block across uneven terrain may require several dozen workers operating in perfect coordination. Monte Padrao required not one stone but thousands. The engineering challenge therefore extended beyond mechanics into logistics. Someone had to organize labor, schedule quarrying, maintain tools, and coordinate construction over many seasons. The layout of the settlement reveals another forgotten technology: planning. Excavation has identified circular houses, internal pathways, defensive gateways, and enclosed activity areas arranged in a pattern that appears intentional rather than random. Circular houses dominate Castro settlements because they distribute structural loads evenly while reducing wall stress, making them particularly resistant to strong Atlantic winds. Their thick granite walls also provide remarkable thermal stability. During summer, they remain cool, while in winter they retain heat generated by central hearths. This represents an impressive adaptation to the humid climate of northwestern Iberia without requiring advanced materials. Yet planning an entire settlement on an irregular granite summit presented far greater difficulties than constructing individual houses. Streets had to accommodate changes in elevation, drainage had to prevent erosion, and houses needed stable foundations despite uneven bedrock. Modern archaeological mapping suggests that movement through the settlement was carefully controlled by narrow passages and gateways, creating defensive choke points that force potential attackers into predictable routes. Such planning resembles military engineering principles later refined by Roman fortifications, but Monte Padrao demonstrates that many of these concepts already existed among indigenous communities before full Roman conquest. Water management introduces another unresolved puzzle. Northern Portugal receives between 1,000 and 1,500 millimeters of annual rainfall depending on elevation. A hilltop settlement exposed to such precipitation faces continuous erosion. Water trapped behind defense walls can gradually destabilize foundations through hydrostatic pressure. Yet Monte Padrao remained occupied for centuries, implying that its builders successfully controlled runoff. Although portions of drainage channels have been identified at Castro settlements across the region, much of Monte Padrao's original hydraulic system has disappeared beneath later occupation layers and natural erosion. Archaeologists therefore understand the results, but not the complete engineering process that produced them. Excavations also reveal evidence of metallurgy. Iron slag, tools, and domestic artifacts indicate that metalworking formed part of the settlement's economy. Iron technology was fundamental to every aspect of construction. Quarrying granite required durable chisels, woodworking demanded axes and adzes. Agriculture depended on iron sickles and plough components. Defensive capability relied upon spearheads and blades. Yet iron production itself required advanced technical knowledge. Bloomery furnaces operated at temperatures approaching 1,200 degrees Celsius, producing spongy blooms that then required repeated hammering to remove slag before becoming usable metal. Every stage demanded precise control of fuel, airflow, furnace design, and timing. None of that knowledge survives in written form because the Castro culture left no engineering manuals. Roman occupation complicates the picture further. Imported ceramics, coins, and building materials demonstrate that Monte Padrao became integrated into the Roman world without losing every element of its indigenous identity. Archaeologists can distinguish Roman artifacts from local ones, but separating Roman engineering influence from existing Castro traditions is far more difficult. Did Roman surveyors improve the settlement's defences, or did they simply inherit an already efficient design? Were drainage systems expanded under Roman administration, or were they largely indigenous innovations? The archaeological layers preserve the physical evidence, but not the decisions behind it. Puig Castellar was discovered in 1902 by Ferran de Segarra on the summit of Turo del Pollo in Santa Coloma de Gramenet, just outside Barcelona, Spain. At 303 meters above sea level, the site covers slightly more than 4,000 square meters and belonged to the Laetani, an Iberian people who occupied this region before Roman control. Archaeological evidence shows that the settlement was occupied from around the 6th century BC until the beginning of the 2nd century BC, when it was abandoned, possibly during the turbulent period connected with the Second Punic War. From this hilltop, the inhabitants could see the coastline, the mouth of the Besós River, the Barcelona plain, and the inland passage towards Valles. This was not a random village. It was a calculated machine of stone, height, visibility, defense, and survival. At first glance, Puig Castellar looks modest. Low stone walls, broken rooms, traces of streets, and a silent summit surrounded by forest. But the deeper mystery begins with its location. The builders did not choose a comfortable flat plain. They built on a difficult hill where every house had to obey the slope. The official archaeological description states that the urban structure adapted to the terrain, and that the houses were raised on terraces to overcome changes in elevation. That single detail reveals a hidden engineering problem. To build a settlement here, the Laetani had to control gravity, soil pressure, rainwater, access routes, and defensive movement without concrete, steel, written engineering manuals, or modern surveying instruments. The most striking feature is not one wall, but the way the entire settlement works as a technical system. The houses were not scattered randomly across the hill. They were organized according to the shape of the summit. with streets and domestic spaces shaped by the terrain. On a hilltop, this is far more complicated than it appears. A badly placed wall would collect water. A badly cut terrace would slide. A poorly aligned street would become useless in rain or attack. Yet Puig Castellar survived for more than 2,000 years, enough for archaeologists to reconstruct its logic. The mystery is not whether the Iberians had advanced technology in a modern sense. The mystery is how much practical engineering knowledge they possessed without leaving behind the drawings, formulas, or instructions that would explain it. The terrace system is the key. To create livable space on uneven ground, ancient builders had to cut, fill, and stabilize platforms. Each terrace needed retaining walls strong enough to resist lateral pressure from earth and stone. These walls were made with local stone and dry stone techniques, meaning stability depended on weight, friction, careful placement, and the interlocking of irregular blocks. In modern engineering, retaining walls must manage overturning, sliding, settlement, and drainage. At Puig Castellar, these same problems existed, but the solutions were empirical. The builders must have known which stones belonged at the base, how much inclination a wall could tolerate, how to lock gaps with smaller stones, and how to prevent water from turning the backfill into a destructive force. Water may be one of the least visible but most important mysteries of the site. A hilltop settlement exposed to Mediterranean storms faces an obvious danger. Rain running downhill can erode floors, undermine foundations, and collapse retaining structures. Yet the settlement was occupied for centuries. This suggests that drainage was built into the layout itself. Streets, thresholds, terrace edges, and stone joints may have worked together to move water away from domestic areas. There is no need to imagine hidden pipes everywhere. The more subtle possibility is even more interesting. The whole village may have been shaped as a drainage device. The slope that made construction difficult also became the force that carried water away, if the builders understood how to guide it. Defense was equally technical. Puig Castellar's position gave it natural protection and control over territory. The Torre Baldovino Museum notes that the site's defensive and territorial conditions suggest it was an important settlement, able to communicate visually with nearby settlements and monitor major routes across the coast, the Bezos mouth, the Barcelona plain, and inland corridors. This means the hill was not only a shelter, it was a surveillance platform. Long before electronic communication, line of sight was a strategic technology. Fire, smoke, movement, and signals could turn a mountain landscape into an information network. The unanswered question is how organized that network was. Did Puig Castellar simply watch the land, or was it part of a coordinated chain of Layatani settlements? Inside the settlement, the mystery becomes social as much as architectural. A terraced hill fort cannot be built by isolated households working without coordination. Someone had to decide where the streets would go, where the walls would stand, and how domestic units would fit into the slope. Someone had to manage labor, stone supply, and repair. The official description states that the urban organization indicates a complex and organized society. That statement matters. Engineering here was not just technical knowledge, it was social order made visible in stone. The layout suggests planning, hierarchy, repeated building rules, and shared maintenance. The missing evidence is the planning system itself. Did they use ropes, sightlines, body-based measurements, wooden markers, or inherited rules passed down by builders? The logistics are equally difficult to explain. Even a small hilltop settlement requires large quantities of stone, timber, clay, food, water, tools, and labor. Puig Castellar covered more than 4,000 square meters. Every wall stone had to be selected, carried, lifted, and fitted. Timber for roofing had to be brought up. Clay and organic materials had to be prepared. Storage, cooking, craft production, and daily movement all had to function inside a restricted summit. There is no sign of machines in the modern sense. The technology was coordination. Human carriers, simple levers, baskets, ropes, paths, and repeated knowledge of how to move materials up a hill without wasting energy. One of the most disturbing discoveries from Puig Castellar adds another layer to the site's meaning. Recent research on severed and nailed skulls from Puig Castellar and Ulla Stret used bioarchaeology, oxygen isotope analysis, and strontium isotope analysis to study human mobility in Iron Age northeastern Iberia. The study examined 7 male skulls from the 2 sites. At Puig Castellar, 3 of the 4 individuals had strontium isotope values that differed significantly from the local reference range, suggesting they were probably not from the local community. This does not directly explain the architecture, but it changes how we understand the settlement. Puig Castellar was not only a quiet farming village, it existed in a world of territorial control, violence, intimidation, and contact with outsiders. The skulls were not randomly selected. Researchers argue that at Puig Castellar their display near the wall may have served as a demonstration of power and coercion, directed both inward and outward. This makes the wall more than a defensive structure. It may have been a political surface, a boundary where architecture and psychological warfare met. A stone wall could stop attackers, but it could also communicate fear. In this sense, the unexplained technology of Puig Castellar includes social engineering, the deliberate use of space, height, visibility, and human remains to control behavior. The economy also raises questions. The museum identifies agriculture as the most important activity, with hunting, livestock, and fishing as complementary activities. But a hilltop settlement is not the easiest place to farm. This suggests that Puig Castellar controlled agricultural land below, rather than depending only on the summit itself. The inhabitants may have moved between fields, slopes, storage areas, and defensive spaces. This creates a technical puzzle of daily logistics. How was grain stored? How was water supplied during dry periods? How were animals managed? How much food could the settlement hold if conflict forced people inside? Archaeology gives fragments, but the full operating system of the settlement remains partly invisible. Rising 153 metres above the Atlantic landscape of northern Portugal, less than 5 kilometres from the coast of Póvoa de Varzim, the ruins of Cividade de Terroso appear as broken circles of stone. Beneath these remains lies one of the oldest and most technically puzzling fortified settlements of the Castro culture. The site stands on Monte da Cividade in Terroso, near the old routes between the Ava River Valley and the Atlantic coast. Official heritage records describe a long occupation from the 8th century BC to the 3rd century AD, making it a place where Bronze Age traditions, Iron Age engineering, and Roman pressure all overlapped in the same hilltop settlement. The municipality of Póvoa de Varzim also identifies it as an Imóvel de Interés Público, a protected heritage site. Its discovery as an archaeological problem did not come from one spectacular treasure alone, but from the slow recognition that this was not a simple village. Archaeological research, especially 20th century excavations, revealed defensive walls, circular houses, occupation layers, and earlier Bronze Age material. In 1981, Armando Coelho excavated ovoid pits containing fragments of 4 vessels from an early phase before the main settlement, evidence that the hill was already part of human activity before the mature, fortified town appeared. What makes Cividade de Terroso mysterious is not fantasy. It is the gap between the tools we imagine for Iron Age communities and the scale of the engineering they actually achieved. The settlement developed from a small late Bronze Age nucleus, and later covered about 4 hectares, according to archaeological studies on Portuguese castros, that is not the size of a temporary refuge. It is the footprint of a planned hilltop centre with enough population, labour and authority to reshape an entire summit. The first technical puzzle is the defensive system. Sources describe 3 lines of walls, while the central platform was protected by 2 parallel walls built with large and medium stones without mortar. The outer faces were regularized, and the space between them was filled with gravel. This is more than a pile of stone, it is a composite structure. 2 stable faces acting like a shell, with smaller material packed inside to absorb pressure, improve mass, and resist collapse. The unanswered question is how the builders controlled stability over long stretches of uneven terrain. Dry stone walls survive only when weight, friction, angle, drainage, and stone selection are balanced correctly. Too much empty space and the wall collapses. Too much pressure behind the face and it bulges outward. Too little drainage and rainwater becomes a hidden weapon inside the structure. At Terroso, the builders used no modern cement, no steel reinforcement, and no written engineering manual that survives today. Yet the system endured through centuries of rain, wind, occupation, abandonment, and later disturbance. The second mystery lies in the location itself. A hilltop gives visibility and defense, but it creates enormous practical problems. Every stone used in a wall, every timber beam, every pot, every grain reserve, and every container of water had to move uphill. The site was close enough to the Atlantic to participate in maritime contacts, and its position helped it become important in coastal trade routes linked to Mediterranean exchange. But that advantage came with a cost. Building a fortified town on a summit demands coordinated labour on a scale we still cannot fully reconstruct. The stones raise a direct engineering question. If part of the material came from the hill itself, quarrying still required extraction, shaping, sorting and placement. If other stones came from nearby slopes, the problem becomes even harder. How are heavy blocks moved? Were they dragged on timber sledges, rolled with wooden levers, lifted by ramps, organised through seasonal labour? Archaeology can expose the wall, but it rarely preserves the vanished machines of wood, rope and human coordination that made the wall possible. The settlement also shows a more subtle kind of planning. Castro towns are often recognised by circular or oval houses, but at Terroso these houses were part of a larger defensive and social structure. A circular house is not technically simple. It needs a stone base strong enough to carry walls, a roof system capable of distributing weight inward, and a floor protected from moisture. The builders had to understand not only stone, but also wood, clay, thatch, smoke movement, and drainage. Each house was a small machine for survival. The mystery deepens because the settlement was not built all at once. It grew over centuries. That means later generations had to understand older walls, reuse earlier spaces, and expand without destroying the logic of the hilltop. This is one of the most difficult things in ancient urbanism, keeping a living settlement functional while rebuilding it. Paths had to remain open, defences had to stay strong, houses had to fit within the wall system. Water still had to move away from living areas. No surviving blueprint tells us how this knowledge was transmitted. Water is one of the most important hidden technologies at Cividad de Terroso. A fortified hilltop can resist enemies, but it cannot resist thirst. The Atlantic climate brings rain, yet rainwater is useful only if it can be collected, directed, stored, or safely removed. If water runs uncontrolled through a settlement, it erodes floors, weakens walls, and turns pathways into channels of mud. The regularized wall faces and gravel-filled cores suggest that the builders had understood drainage not as decoration, but as survival engineering. There is also the question of regional power. Archaeological studies describe Terroso as one of the settlements that gained importance because of its position in long-distance communication and commerce. It was not isolated from the world. the wider Castro region interacted with Atlantic and Mediterranean networks, and later traditions connect the area with gold, tin, and high-value objects. Jewellery associated with nearby Laundos shows advanced techniques such as filigree and granulation, methods comparable to Mediterranean metalworking traditions. This does not prove that every technique at Terroso was imported. In fact, the more interesting possibility is hybrid technology. Local builders may have used native Atlantic dry stone methods while absorbing ideas, objects, and status symbols from wider trade routes. The result was not a copy of a Mediterranean town. It was a hill fort adapted to the climate, geology, and social structure of northwest Iberia. That makes the engineering harder to explain because it was not one simple tradition. It was a fusion of local knowledge and external contact. Then came Rome. Official sources place the occupation of the hill from the 8th century BC into the 3rd century AD, which means the settlement lived through the period of Roman expansion and later Roman influence. Some accounts connect the destruction or transformation of the Castro world with Roman conquest in the 2nd century BC, especially after the Lusitanian conflicts. But the archaeological story is not only destruction, it is also adaptation. Roman presence did not erase every older technique immediately. In places like Terroso, native structures and Roman period occupation overlapped. That overlap creates another technical mystery. Why did some indigenous building habits survive even after contact with Roman engineering? Rome had roads, concrete surveyors, and military construction systems, yet local stone architecture remained meaningful. Perhaps it was because the Castro builders had already solved the local problems better than outsiders could. Atlantic rain, granite terrain, hilltop defense, and community-based construction. A Roman technique was not automatically superior in every landscape. Rising above the valleys of Humada in Burgos, northern Spain, La Yulana stands like a natural fortress. It was not simply built, it was chosen. The site began to be documented through archaeological work in the late 1990s, when surveys and excavations revealed that this was not a small hill fort, but one of the largest Iron Age fortified settlements ever identified in the Iberian Peninsula. Archaeological publications describe La Yulana as covering about 586 hectares in total, with around 285 hectares on the upper platform and another 301 hectares in the surrounding natural depression, known as the Cinto. What makes La Yulana so disturbing is its scale. Most Iron Age hill forts in northern Iberia were far smaller, often occupying hilltops, ridges, or defensible spurs. La Yulana was different. It sat on a vast limestone mesa surrounded by cliffs, with natural rock faces acting as defensive walls long before human hands added masonry. The upper settlement alone covered roughly 285 hectares, making it the largest known settlement of the Second Iron Age in the Iberian Peninsula and one of the largest in Europe. The first mystery is not how they built the wall, but how they understood the mountain. The people who occupied La Yulana did not try to dominate the landscape with endless construction. They read it. The steep cliffs, the natural moat, the limited access routes, and the high visibility over the surrounding territory were all turned into parts of one defensive machine. This was not primitive shelter, it was landscape engineering. A fortress of this size required knowledge of movement, wind, slope, stone, and visibility. Without modern maps, drones, or surveying instruments, someone had to understand where enemies could climb, where animals could pass, where water might collect, and where people could live safely. Excavations identified hundreds of structures inside the settlement. One summary of the site notes around 267 architectural structures, as well as several steep access routes. These were not the traces of a temporary refuge. They suggest a complex occupation with domestic buildings, storage areas, routes, walls, and zones of activity. The ruins force a difficult question. Was La Yulana a permanent urban centre, a seasonal stronghold, a political refuge, or a strategic capital used in times of pressure? The answer remains uncertain because the physical scale is almost too large for the known evidence. Its defensive logic is especially impressive. The plateau was protected not only by man-made walls, but by geology itself. The surrounding cliffs reduced the number of vulnerable points. The Cinto, a natural depression around the mesa, worked almost like a gigantic moat. In military terms, this meant the builders didn't need to enclose the entire mountain with continuous high walls. They only had to strengthen the weak points, control the entrances, and use the terrain as an ally. This kind of planning shows that Iron Age communities in northern Spain were capable of strategic thinking at a landscape scale. But the greatest technical mystery of La Yulana is water. A settlement of this size on a limestone plateau should not have been easy to sustain. Limestone is porous. Rainwater often disappears quickly into cracks, fissures, caves, and underground channels. On a karstic landscape, surface streams can be rare or seasonal. That creates a paradox. La Yulana was enormous, defensible, and carefully positioned, but it sat on terrain where permanent water supply is difficult to prove archaeologically. If hundreds or thousands of people lived there, even seasonally, they needed drinking water, water for cooking, animals, craft production, and possibly metallurgy. The numbers make the problem sharper. A person needs several litres of water per day just to survive, and far more for cooking, washing, and work. Cattle, which appear to have played an important role in the economy of the settlement, require many times more. Studies of La Yulana's economy describe livestock as central, especially cattle, with sheep, goats, pigs, and horses also present. If the settlement held a large human population and herds, the daily water demand could have reached thousands or even tens of thousands of litres. Yet the visible archaeological evidence does not give a simple answer. One possibility is rainwater harvesting. The plateau could have collected seasonal rain in depressions, rock-cut basins, clay-lined pits, or artificial reservoirs. In many ancient upland settlements, water was managed through channels, cisterns, storage pits, and carefully selected low points. At La Yulana, the natural limestone surface may have been both a problem and a tool. Water could vanish into cracks, but if people understood the rock, they may have used natural hollows and sealed surfaces to slow runoff and capture it. The missing evidence is the exact system, where the water was stored, how it was protected from evaporation, how it was kept clean, and how long it could support the population during dry periods. Another possibility is that the people of La Yulana understood the hidden hydrology of karst. Limestone plateaus often contain underground water movement that is invisible from the surface. Springs may emerge at the foot of the slope rather than on the summit. The name Yulana itself has been discussed as pre-Roman, and one archaeological study notes a possible connection with a route linked to emergence or flowing water. That linguistic clue does not solve the engineering question, but it adds a strange possibility. Perhaps water was more central to the identity of this place than the surviving ruins reveal. If springs existed below the plateau, then the settlement had another problem: transport. Carrying water uphill is exhausting. For a small refuge it is possible. For a huge oppidum it becomes a logistical system. People would need paths, containers, labour organisation, and repeated daily movement between the water source and the settlement. If the site was used as a defensive refuge during conflict, then access to external springs would be dangerous during siege. That means La Yulana either had internal storage, hidden protected access to water, or a population pattern that was more complex than a simple permanent city. This is why the water mystery matters. It is not just about survival. It changes the meaning of the entire site. If La Yulana had an advanced rainwater collection system, then it was an engineered highland settlement capable of supporting large numbers on a difficult plateau. If it depended on springs below, then it was a fortress whose strength had a hidden weakness. If it was occupied seasonally, then the huge area may not represent a dense city, but a flexible landscape of gathering, livestock management, storage, and defense. Each answer creates a different La Yulana. The stonework adds another layer. Building on limestone means the builders had access to local stone, but using local material does not make the work simple. Stone had to be selected, moved, shaped, stacked, repaired, and stabilized. The upper platform and surrounding defensive zones show that La Yulana was not created by scattered household effort alone. It required coordination. Walls, access points, and internal structures imply planning over time. The technology here was not a lost machine. It was social engineering, organized labor, shared decisions, and practical knowledge transmitted without written manuals. The site also raises questions about metallurgy. A recent archaeometric study of metallic remains from La Yulana highlights the importance of analyzing metal objects to understand technological activity at the settlement. Metal tools would have mattered for cutting, woodworking, weapon repair, farming, and possibly quarrying. But metallurgy requires fuel, ore or imported metal, water, controlled heat, and skilled labor. In a highland site where water was already a challenge, every trace of metal production becomes part of a wider technical puzzle. How much was produced on site? How much was brought in? Did La Yulana function as a regional power center connected to trade networks across northern Iberia? The location suggests that control was as important as defense. La Yulana overlooked routes through the landscape and stood near the frontier zones of northern Iberian peoples before Roman domination. A fortified settlement of this size was not just a place to hide. It was a statement. It controlled movement, animals, resources, and memory. The cliffs made it hard to attack, but the height also made it visible. Anyone crossing the valleys would have known that a major power occupied the plateau above them. In Sulusaray, Tokat province, central Turkey, the ancient city of Sebastopolis lies buried beneath fields and a modern town. Excavations that began in the 20th century and have continued in recent decades have uncovered only a fraction of what once stood here. Roman baths, monumental columns, streets, mosaics, inscriptions, water channels, and public buildings. Yet archaeologists estimate that much of the ancient city still remains underground. This incomplete picture makes Sebastopolis less of a finished archaeological site and more of an engineering puzzle. Every trench reveals sophisticated Roman construction, but every discovery also raises new questions about technologies that have not been fully reconstructed. The first mystery begins with the ground itself. Sebastopolis was established in the fertile valley of the Yeşilırmak river system, in a region influenced by the ***, North Anatolian fault ***, one of the world's most active strike-slip fault systems. Modern geology estimates that the fault stretches for roughly ***, 1,500 kilometers ***, producing numerous destructive earthquakes throughout history. Building a large urban center in such an environment appears surprisingly risky, yet Roman engineers laid out streets, bath complexes, temples, administrative buildings, and drainage systems that survived repeated seismic events for centuries. Archaeologists can identify rebuilding phases in masonry, but they still cannot fully explain how Roman surveyors selected stable ground without modern geophysical instruments. Did they recognize hidden fault lines through generations of empirical observation? Did they deliberately avoid unstable sediments, or reinforce foundations using techniques now lost. The surviving structures suggest practical seismic knowledge, but the exact methods remain uncertain. Water forms the second and perhaps greatest engineering mystery. Sebastopolis developed around abundant mineral-rich springs that still flow today. For the Romans, thermal water represented not only luxury but also medicine, religion, and urban infrastructure. Constructing baths required much more than simply diverting a spring. Engineers had to calculate gradients, regulate pressure, separate clean water from wastewater, prevent sediment accumulation, and maintain constant flow despite seasonal variation. Excavations have exposed portions of channels and bath complexes, but the complete hydraulic network has never been uncovered. Many conduits disappear beneath unexplored sections of the city. Without the missing segments, archaeologists cannot reconstruct exactly how water entered the baths, how temperatures were regulated, or how excess mineral deposits were controlled before pipes became blocked. Modern hydrogeology explains how thermal springs emerge, but it does not explain every engineering decision made by Roman builders nearly 2,000 years ago. The bath complex itself introduces another unresolved technological question. Roman bathhouses depended on the famous hypocaust heating system, where furnaces pushed hot air beneath suspended floors supported by hundreds of small brick pillars. The heated air then circulated inside hollow wall tiles before escaping through roof vents, creating remarkably even indoor temperatures. Across the Roman world, some bathhouses maintained interior temperatures exceeding *** 40 degrees Celsius ** in hot rooms, while adjacent pools remained significantly cooler. Achieving this required precise airflow control rather than simple heating. At Sebastopolis, archaeologists have uncovered evidence of bath architecture, but much of the subfloor system remains buried or damaged. Consequently, researchers still debate the exact furnace arrangement, fuel consumption, airflow design, and maintenance techniques that allowed continuous operation in a city supplied by mineral-rich thermal water. Scaling inside pipes and channels should have required frequent cleaning, yet there is little direct evidence explaining how this maintenance was organized. Equally intriguing is the mystery of Roman mortar. Several surviving walls at Sebastopolis continue standing despite centuries of earthquakes, groundwater movement, and seasonal freezing. Roman concrete and lime mortars have become famous because many structures remain structurally sound after nearly 2 millennia. Recent materials science has shown that certain Roman mortars contained ***, lime clasts ***, that promoted self-healing through secondary calcium carbonate formation when cracks developed. Other studies demonstrated that volcanic materials could generate durable hydraulic cement capable of hardening underwater. However, central Anatolia does not possess identical geological resources to Italy. This raises an important question. Did builders at Sebastopolis adapt Roman recipes using local volcanic ash, crushed ceramics, river sand, or completely different aggregates? Chemical analyses of some Roman mortars elsewhere reveal enormous regional variation, suggesting there was never a single universal formula. The precise composition used at Sebastopolis has not yet been comprehensively reconstructed, leaving open the possibility that local craftsmen developed their own durable mixtures suited to Anatolia's climate and geology. Urban planning presents another puzzle. Excavated streets reveal the familiar Roman preference for geometric organization, yet the city occupies terrain that is neither perfectly flat nor perfectly regular. Surveyors without laser instruments somehow established long straight alignments, building orientations, drainage gradients, and public spaces that function together as one coherent urban system. Roman surveyors certainly employed instruments such as the ****, groma ****, shorebaits ****, and measuring rods. But exactly how these tools were adapted to Sebastopolis' uneven landscape remains unknown because only fragments of the street network have been exposed. Remote sensing suggests that substantial portions of the ancient city remain buried beneath agricultural land and the modern settlement. Until larger excavations become possible, researchers cannot determine whether the visible streets represent the entire urban plan or merely one district within a much larger engineered city. Transportation poses yet another unresolved engineering challenge. The monumental architecture required thousands of tons of stone, brick, lime, timber, roof tiles, and marble. Some architectural blocks weigh several tons each, yet no complete reconstruction exists, showing how these materials reached the construction sites. Archaeologists have identified local stone sources in the wider region, but the logistics remain uncertain. Roman engineers elsewhere relied on wheeled carts, sledges, rollers, cranes, compound pulleys, and carefully prepared roads. Which combination was employed at Sebastopolis is still debated because the supporting infrastructure, quarries, workshops, transport routes, and construction yards has only been partially identified. Every missing workshop represents missing technological knowledge. The city's drainage system may be even more impressive than its visible monuments. Roman cities depended on hidden infrastructure. Streets required gradients sufficient to remove stormwater while preventing erosion. Bathhouses discharged enormous quantities of used water. Latrines required continuous flushing. Foundations had to remain stable despite constant groundwater movement. Excavations at Sebastopolis have exposed sections of drains, but no complete underground network has yet been mapped. Without that network, engineers cannot calculate the designed discharge capacity or determine whether the Romans incorporated overflow systems capable of handling seasonal floods. Modern hydraulic modelling depends on complete layouts, and Sebastopolis simply has not revealed enough of its buried infrastructure. El Shinal is one of the most mysterious Inca cities ever built outside Peru. Located in the Quimivil Valley of Catamarca Province, northwestern Argentina, the site lies more than 1,500 kilometers south of Cusco, the capital of the Inca Empire. Yet despite this enormous distance, archaeologists discovered a city planned according to core Inca principles, complete with a monumental ceremonial plaza, a sacred Ushnu platform, terraced hills, administrative buildings, storage facilities, and connections to the vast Chapak-Nan road network. The greatest mystery is not that the city existed, but how Inca engineers successfully recreated a sophisticated imperial center so far from the heart of their civilization while employing technologies that remain only partially understood today. The ruins became known to modern researchers during the 19th century, but systematic archaeological investigations expanded significantly during the 20th century under Argentine scholars, including Alberto Rex Gonzalez and subsequent research teams. Excavations revealed that El Shinal was likely founded during the late 15th century, possibly under the expansion campaigns of Tupac Inca Yupanqui or Huayna Capac. Covering roughly 30 hectares, the settlement quickly emerged as one of the most important Inca administrative centers in southern South America. Yet every major discovery seemed to create new questions rather than provide answers. One of the greatest engineering mysteries concerns the decision to build El Shinal itself. Most empires lose administrative control as distance increases because communication slows, transportation becomes difficult, and logistics become increasingly complex. The Roman Empire experienced these challenges, and the Han dynasty faced similar limitations. Yet the Inca successfully established a highly organized center more than 1,500 kilometers from Cusco. Without wheeled transport, iron tools, horses, or written bureaucratic records comparable to those used in Eurasian civilizations, the Inca somehow maintained authority across an empire stretching approximately 4,000 kilometers along the Andes. El Shinal demonstrates that this system worked remarkably well. Archaeologists have identified architectural layouts closely resembling those found near Cusco itself, and the precision of this replication suggests centralized planning, standardized construction methods, and highly effective communication networks. The exact mechanisms that allowed such control remain debated. Modern comparisons help illustrate the scale of this achievement. The distance separating El Shinal from Cusco is comparable to the distance between Paris and Athens, and maintaining administrative cohesion across such territory without modern communication technologies would challenge even many pre-industrial states. Perhaps the most fascinating mystery involves astronomical engineering. Several studies indicate that the city's orientation was not random. The central plaza, ceremonial structures, and surrounding sacred hills appear to interact with solar movements throughout the year. Researchers have proposed that the two prominent terraced hills flanking the city may have served as astronomical reference points. This pattern appears elsewhere in Inca architecture. Machu Picchu, Cusco, and numerous ceremonial centers contain alignments associated with solstices and equinoxes, and El Shinal seems to belong to the same tradition. The engineering challenge is significant because determining precise solar positions requires long-term observation. Modern surveyors rely on compasses, GPS systems, laser instruments, and computer models, yet Inca engineers possessed none of these technologies. Nevertheless, they achieved alignments accurate enough to remain recognizable centuries later. Some archaeologists argue that repeated observations conducted over generations allowed Inca specialists to construct reliable astronomical calendars. Others suggest that sophisticated surveying techniques may have existed but disappeared after the Spanish conquest. No definitive explanation has been established. At the center of El Shinal stands a monumental Ushnu platform. Similar structures appear throughout the Inca world, but El Shinal preserves one of the best examples discovered outside Peru. The structure appears deceptively simple, yet its position dominates the entire city. From its elevated surface, observers could view major sections of the settlement as well as surrounding natural landmarks. The mystery concerns its exact purpose. Some researchers interpret the Ushnu as a ceremonial platform used during state rituals. Others argue that it functioned as an astronomical observation point. A third hypothesis suggests that it served both political and scientific purposes simultaneously. Measurements indicate that several sightlines from the platform correspond with significant landscape features. Whether these alignments were symbolic, astronomical, administrative, or all three remains uncertain. The situation resembles debates surrounding Stonehenge in Britain and Chanquillo in Peru, where monumental structures often survive while the knowledge explaining their precise function disappears. El Shinal was not built on naturally flat ground. The settlement occupies a landscape of uneven terrain, surrounded by hills and seasonal watercourses. To create the city's organized appearance, builders modified large portions of the natural environment. Terraces were constructed, slopes were stabilized, drainage systems were established, public spaces were leveled, and ceremonial hills were reshaped. Such work required extraordinary quantities of labor. Modern engineers would employ bulldozers, excavators, grading equipment, and surveying instruments, whereas the Inca relied primarily on stone tools, wooden implements, rope, and human labour. Researchers estimate that major Inca construction projects often involved thousands of workers organised through the Maritime labour system. Yet the methods used to coordinate earth-moving operations at El Shinal remain poorly documented. The city demonstrates landscape engineering on a scale comparable to agricultural terracing systems elsewhere in the Andes, some of which moved hundreds of thousands of cubic meters of material. El Shinal may represent a similar achievement in urban planning. Water determined survival throughout the Andes. Although El Shinal receives more rainfall than many desert regions controlled by the Inca, seasonal fluctuations still created challenges. Archaeologists have identified evidence of channels, drainage features, and hydraulic planning integrated into the city's layout. The mystery lies in the sophistication of these systems. Throughout the Inca world, engineers designed water networks capable of functioning for centuries. Machu Picchu contains drainage systems that continue to operate today, while Tipon near Cusco preserves hydraulic works that remain remarkably efficient despite being more than 500 years old. El Shinal appears to have incorporated similar principles. Engineers successfully controlled runoff, protected buildings from erosion, and supplied water to critical areas of the settlement. Yet many hydraulic components remain buried or poorly understood, and future excavations may reveal a far more complex system than currently recognized. El Shinal was connected to the Capac Nan, the vast Inca road system extending across western South America. This network exceeded 30,000 kilometers in total length. By comparison, many major Roman roads collectively covered similar scales across Europe and the Mediterranean. The mystery is how the Inca maintained such a system without wheeled transport. Messengers known as chasqui carried information between relay stations. Goods moved through coordinated labor networks, and administrative commands traveled across mountains, deserts, and valleys. El Shinal functioned as one of the southern hubs within this immense infrastructure system. Modern logistical models suggest that maintaining reliable communication across thousands of kilometers without written dispatches should have been extremely difficult. Yet the archaeological evidence demonstrates that the system operated successfully for generations. Exactly how information, taxation records, labor obligations, and political decisions were coordinated remains one of the greatest unanswered questions in Inca studies. Only a portion of El Shinal has been thoroughly investigated. Excavations have revealed plazas, administrative compounds, ceremonial structures, and residential areas. However, large sections remain unexplored. This creates a fascinating possibility. The visible city may represent only a fraction of the original settlement. Ground-penetrating radar surveys at archaeological sites around the world have repeatedly revealed hidden architecture invisible from the surface. Similar discoveries transformed understanding of Angkor in Cambodia, Teotihuacan in Mexico, and numerous Roman cities throughout Europe. If comparable investigations are conducted extensively at El Shinal, researchers may uncover additional roads, workshops, storage facilities, elite residences, or hydraulic structures. Such discoveries could fundamentally change current interpretations of the site. El Perutal, hidden within the mountains of Huila in southern Colombia, contains a mystery that should not exist. More than 1,000 years after its craters disappeared, traces of red, yellow, black, and white paint still cling to its stone statues. While the colours of most ancient monuments vanished centuries ago, the pigments of El Perutal survived. El Perutal forms part of the larger San Agustin Archaeological Park, a UNESCO World Heritage Site. Archaeological investigations throughout the 20th century revealed a ceremonial complex containing tombs, artificial mounds, and some of the only known polychrome statues from the ancient San Agustin civilization. These discoveries transformed El Purutal into one of the most important archaeological mysteries in South America. The greatest mystery of El Purutal is not the statues themselves, but the paint. Throughout history, colour has proven surprisingly fragile. The vibrant pigments that once decorated Greek temples have almost entirely disappeared. Many Roman sculptures lost their original paint layers, and even murals preserved inside protected structures often suffer severe degradation after centuries of exposure. Yet, at El Purutal, pigments remain visible after approximately 1,000 to 1,500 years. The statues display traces of red, yellow, black and white coloration. Scientific analysis suggests that the colours were likely derived from natural mineral sources. Red pigments may have originated from iron oxides similar to hematite. Black pigments may have contained manganese compounds or charcoal-based materials. Yellow pigments were likely produced from iron-rich minerals, while white pigments may have involved clay or mineral-based substances. The real mystery is not the source of the pigments, but their survival. El Purutal lies in a tropical environment characterized by rainfall, humidity, biological activity, and significant temperature fluctuations. Such conditions normally accelerate weathering. Rainwater penetrates stone surfaces, organic growth damages pigments, and ultraviolet radiation breaks down molecular structures. In many comparable environments, ancient paint survives only in microscopic traces. Yet portions of the El Purutal pigments remain visible to the naked eye. Researchers still cannot fully reconstruct the original manufacturing process. What binding agents were used? How were the pigments attached to the stone? Was the stone chemically prepared before painting? Were multiple protective layers applied? No surviving document answers these questions. The situation resembles other ancient technological mysteries. Scientists studying Roman concrete eventually discovered that volcanic ash contributed to the material's remarkable durability, while researchers investigating Egyptian pigments found sophisticated chemical knowledge behind supposedly simple colours. El Purutal may represent another example of ancient materials, science whose underlying principles remain only partially understood. The statues stand as physical proof that the San Agustin people possessed practical knowledge of mineral chemistry, surface preparation, and long-term durability. The results survived, but the instructions disappeared. Most people imagine ancient stone monuments as monochrome objects, yet archaeology increasingly reveals the opposite. Ancient Greek temples were painted, Roman statues were painted, and Egyptian monuments were painted. El Purutal demonstrates that the San Agustin civilization followed a similar tradition. The statues were not merely carved, they were transformed into multicolored visual displays designed to communicate symbolic messages. This required several technological steps. First, suitable stone had to be selected and shaped. Second, surfaces needed preparation to receive pigments. Third, colors had to be produced from mineral resources. Fourth, pigments had to be applied in a manner capable of surviving environmental exposure. Each step required specialized knowledge. Modern conservators often spend years studying the interaction between pigments and stone surfaces. The artisans of El Purutal achieved comparable results without modern chemistry, microscopes, or laboratory equipment. How they perfected the process remains uncertain. The most famous statues at El Purutal are often interpreted as representations of life and death. The problem is that nobody knows for certain. The figures combine human and animal characteristics. Some display jaguar-like features, while others appear to incorporate symbolic elements associated with spiritual transformation. This ambiguity is one of the defining characteristics of San Agustin art. The civilization left no deciphered writing system. Unlike the Maya, whose inscriptions preserve historical records, the San Agustin people left primarily stone monuments. As a result, archaeologists must interpret symbolism without textual explanations. Were the figures gods? Were they ancestors? Were they rulers transformed into supernatural beings? Or were they shamans mediating between the physical and spiritual worlds? The statues remain silent. El Perutal was not simply a collection of sculptures. The site formed part of a carefully engineered ceremonial landscape. Archaeologists discovered artificial mounds, burial structures, retaining systems, pathways, and monument platforms integrated into the surrounding terrain. Creating such a landscape required substantial labour. Workers moved enormous quantities of soil to construct elevated areas. Slopes had to be stabilised, drainage systems needed management, and burial chambers had to be protected from collapse. These activities reveal a level of organisation far beyond what casual observers might expect. Modern earth-moving equipment can reshape landscapes in hours, but ancient builders relied entirely on human labour. The scale of modification suggests coordinated planning over extended periods. Who directed these projects remains unknown. The statues themselves present another engineering puzzle. Many San Agustin sculptures weigh several tons, and some stand more than 4 meters tall. Transporting such objects would challenge even modern crews operating in rugged mountain environments. The terrain surrounding El Perutal consists of hills, valleys, and steep slopes. No surviving roads reveal the exact transportation routes. No ancient diagrams explain the process, and no written instructions survive. Researchers generally believe that teams of workers moved the stones using ropes, wooden rollers, sledges, and carefully organised labour. The problem is that the details remain speculative. Ancient societies across the world repeatedly solved transportation challenges that continue to impress engineers today. The builders of Stonehenge moved stones weighing up to 25 tons across hundreds of kilometres. Egyptian workers transported granite blocks exceeding 60 tons, and in Peru, Inca builders moved massive masonry elements across mountainous landscapes. El Perutal belongs to this tradition of unexplained logistical achievement. The statues exist because the problem was solved. How it was solved remains uncertain. Perhaps the strangest mystery is that so much survives and yet so little is known. The broader San Agustin region contains more than 500 statues, numerous tombs, ceremonial structures, and extensive archaeological remains. This represents centuries of cultural activity, yet the people responsible left no readable historical record. Their language vanished, their political system vanished, their names vanished, and their technical manuals vanished. What remains are the products of their knowledge. Archaeologists can measure the monuments, analyze the pigments, map the structures, and reconstruct construction sequences. But the intellectual framework behind the civilization remains largely invisible. This creates a paradox. The evidence demonstrates significant expertise in sculpture, engineering, landscape modification, and materials technology. Yet the civilization itself remains one of the least understood major archaeological cultures of pre-Columbian South America. What do you think made the pigments of El Perutal survive for more than 1,000 years? Was it a lost painting technology, a unique combination of minerals, or knowledge that has completely vanished from history? Share your thoughts in the comments below. Villa de Leyva, Colombia. Hundreds of years before European astronomers brought telescopes to South America, an unknown group of engineers from the Muisca civilization erected dozens of stone pillars across a high-altitude valley. Today, archaeologists call the site El Infiernito. What appears at first glance to be a simple arrangement of stones may actually represent one of the most sophisticated astronomical systems ever built in pre-Columbian America. Spanish chroniclers first described the stone field during the 16th century after the conquest of the Muisca people. Systematic archaeological investigations began centuries later, revealing rows of standing stones, ceremonial structures, burials, and evidence that the site functioned as both a religious centre and a possible astronomical observatory. Yet one question remains unresolved. How accurate was El Infiernito really? This is the greatest mystery of El Infiernito, and the reason the site is often compared to Stonehenge. The surviving stone columns are arranged in parallel rows extending across the landscape. Researchers discovered that several alignments correspond closely to the position of sunrise during the solstices and equinoxes. If intentional, this would mean that the builders could track the annual movement of the sun with remarkable precision. To understand the significance of this achievement, consider the challenge involved. The Earth's axis is tilted approximately 23.5 degrees. As a result, the sunrise position shifts continuously along the horizon throughout the year. Detecting this movement requires repeated observations over many years. A single observation is insufficient. Builders must establish fixed reference points, identify recurring patterns, and distinguish long-term cycles from seasonal variation. Modern observatories solve this problem using calibrated instruments. The builders of El Infiernito had none of these tools. No telescopes, no metal surveying equipment, no optical lenses, and no written trigonometric tables. Yet the stone alignments suggest that someone understood the movement of the sun well enough to transform astronomical observations into permanent architecture. The mystery becomes even deeper when considering the site's latitude. Located near 5 degrees north, seasonal changes in solar position are less dramatic than at higher latitudes. Detecting solstice positions is therefore more difficult than in places such as Stonehenge in England. Some archaeologists estimate that achieving reliable solar alignments would require observations spanning multiple decades. The builders may have recorded sunrise positions year after year, gradually refining the placement of each stone until a functioning solar calendar emerged. But no evidence has been discovered explaining exactly how this process worked. Did they use wooden sighting posts that later decayed? Did they employ shadow tracking methods similar to those used in ancient Egypt? Did generations of observers preserve astronomical knowledge through oral traditions? The stones remain silent. The arrangement of El Infiernito appears deceptively simple. In reality, creating long rows of aligned stones requires advanced surveying techniques. Even small errors accumulate rapidly over distance. A deviation of only 1 degree can shift a sightline by several meters across a long alignment. Modern engineers use transits, laser levels, GPS systems, and mathematical calculations. The Muisca possessed none of these technologies, yet the stones exhibit an organization suggesting careful planning rather than random placement. Experimental archaeologists have demonstrated that surprisingly accurate alignments can be produced using only ropes, wooden stakes, and observations of shadows cast by the sun. However, reproducing the precision potentially observed at El Infiernito remains challenging. The exact surveying methods employed by the builders remain unknown. Constructing a solar observatory requires enormous effort. Each stone had to be quarried, transported, positioned, and stabilized. The process demanded labor, planning, and social organization. Why invest such resources? One explanation involves agriculture. The Muisca economy depended heavily on crops such as maize, potatoes, quinoa, and beans. Accurate knowledge of seasonal cycles would have provided significant advantages for planting and harvesting. Another possibility involves religion. Throughout the ancient world, astronomy and spirituality were deeply connected. Egyptian temples, Maya observatories, and Mesopotamian ziggurats all incorporated celestial alignments into sacred architecture. El Infiernito may have served a similar purpose. The ability to predict solstices and seasonal transitions could have reinforced religious authority, transforming astronomical knowledge into political power. The largest surviving pillars are not as massive as the megaliths of Stonehenge, where some stones exceed 25 tons. Nevertheless, many El Infiernito pillars still weigh hundreds of kilograms or more. Transporting such stones without wheeled vehicles presents a substantial engineering challenge. The Muisca had no horses, oxen, or large draft animals before European contact. Human labour alone would have been responsible for moving the stones. Archaeologists propose several possibilities, including wooden rollers, sledges, rope systems, earthen ramps, and collective labour teams. All are technically plausible, yet no direct archaeological evidence has revealed which method was actually used. The engineering process remains largely invisible. Spanish accounts describe the Muisca as possessing one of the most sophisticated calendrical systems in pre-Columbian South America. Historical records suggest they tracked complex cycles of time and maintained an advanced numerical system. This is particularly significant because astronomical observation and mathematics are inseparable. A functioning solar calendar requires counting days, recognizing recurring patterns, and predicting future events based on previous observations. The existence of El Infiernito suggests a body of mathematical knowledge that once existed but largely vanished following the Spanish conquest during the 16th century. Today, archaeologists can identify the results of that knowledge. The knowledge itself is mostly gone. For decades, researchers debated the site's primary purpose. The astronomical interpretation is compelling, but El Infiernito also contains evidence of ritual activity, ceremonial practices, and burials. Some stone pillars possess obvious symbolic and fertility-related characteristics. Others appear associated with sacred spaces rather than purely observational functions. This raises an important possibility. What if the site was never intended to be only an observatory? Many ancient monuments served multiple functions simultaneously. Stonehenge functioned as a ceremonial centre, burial site, and astronomical marker. The Temple of Karnak incorporated both religious and solar alignments. Maya observatories combined political, ceremonial, and scientific functions. El Infiernito may belong to this same category, a place where astronomy, religion, politics, and social organization merged into a single system. Was El Infiernito primarily an astronomical observatory, or was astronomy simply one part of a much larger system of religion and power? North Yorkshire, England. Along a remote stretch of cliffs facing the North Sea, an industry emerged in the 17th century that produced one of the most valuable chemical substances in Europe. The mystery is not what they made. The mystery is how they knew where to find it. The remains of Yorkshire's alum works were documented throughout the 18th and 19th centuries, but systematic archaeological investigation accelerated during the 20th century. Researchers uncovered massive burning platforms, extraction pits, reservoirs, stone tanks, transport routes, and industrial waste deposits stretching for kilometres along the coastline. These ruins revealed that North Yorkshire once hosted one of the largest chemical industries in Europe before the Industrial Revolution. This is the greatest mystery of all. Alum, chemically known as hydrated potassium aluminum sulfate, was one of the most important industrial chemicals in pre-industrial Europe. It was essential for fixing dyes in textiles, preserving leather, manufacturing medicines, and supporting numerous crafts. During the 16th century, Europe depended heavily on alum imported from Italy, particularly from the papal-controlled deposits at Tolfa. Then something remarkable happened. Around the late 16th century, English entrepreneurs discovered that the dark Jurassic shale exposed along the cliffs of North Yorkshire contain the ingredients necessary to manufacture alum. The question that continues to puzzle historians is simple. How did they know? The Yorkshire coast contains millions of tons of black shale, and most of it appears unremarkable. To the untrained eye, it looks no different from countless other rock formations across Britain. Yet hidden within specific layers were sulfur-bearing minerals, particularly pyrite, capable of producing the chemical reactions required for alum production. No geological surveys existed, no chemical laboratories existed, and no modern mineral analysis existed, yet someone identified the correct rock. One theory suggests that English agents secretly obtained industrial knowledge from Italy. Historical records indicate that experienced alum workers from the continent may have been recruited to England despite efforts by foreign powers to protect their monopoly. Another theory argues that local observers noticed similarities between Yorkshire shale and alum-bearing rocks described elsewhere in Europe. Neither explanation fully solves the mystery. Finding a useful rock formation is one challenge, but identifying thousands of hectares of productive shale among vast coastal exposures is another. Modern mining companies employ geologists, geochemical testing, satellite imagery and drilling programs. The first Yorkshire alum producers had none of these tools. The situation is comparable to finding a hidden copper deposit without geology, locating petroleum without seismic surveys, or identifying uranium without radiation detectors. Somehow, knowledge existed before the science needed to explain it. Even today, historians cannot reconstruct the exact process through which Yorkshire's alum deposits were first recognised. After extraction, the shale underwent a process that appears astonishing even by modern standards. Workers piled enormous quantities of rock into vast mounds, sometimes reaching several meters in height and extending across large areas. These piles were then ignited and allowed to burn continuously, not for days, not for weeks, but for months. Historical accounts suggest that some burning cycles lasted between 6 and 12 months before completion. The objective was to oxidize pyrite contained within the shale. During combustion, sulfur compounds reacted with oxygen, generating sulfuric acid and initiating complex chemical transformations necessary for alum production. The mystery lies in control. Modern industrial roasting operations rely upon thermometers, airflow monitoring, automated systems, and chemical analysis. Yorkshire workers possessed none of these technologies. If temperatures became too low, reactions would remain incomplete. If temperatures became too high, valuable compounds could be destroyed. Yet generation after generation managed to achieve the desired result. Archaeological evidence indicates that workers carefully managed ventilation pathways within the burning heaps. However, researchers still debate exactly how temperatures were monitored and controlled. Much of this expertise appears to have been transmitted orally and vanished when the industry declined. Perhaps the most fascinating aspect of the Yorkshire alum industry is that it operated successfully before the scientific revolution fully explained the processes involved. The first commercial alum works appeared decades before modern chemistry emerged as a formal scientific discipline. Workers understood procedures, but they did not necessarily understand molecules. They understood outcomes, but they did not understand atomic structure. They knew which materials to combine, how long to burn the shale, how to process solutions, and when crystallization was complete. But concepts such as oxidation reactions, molecular bonds, and chemical equilibrium remained centuries away. This situation resembles other technological mysteries throughout history. Roman engineers produced durable concrete without understanding modern materials science. Medieval blacksmiths manufactured Damascus steel without knowledge of crystallography. The builders of the Antikythera mechanism created an analog computer nearly 2,000 years before modern mechanical engineering emerged. Yorkshire alum workers belong to the same tradition of practical expertise, exceeding contemporary scientific theory. Once roasting was complete, the shale had to be processed using large quantities of water. The solution sounds simple, but the reality was not. Many alum works occupied steep coastal locations where terrain presented major engineering challenges. Water had to be collected, directed, stored, and distributed across multiple processing stages. Archaeologists have identified extensive systems including reservoirs, channels, settling tanks, leaching pits, and evaporation facilities. Gravity performed much of the work. Instead of relying upon pumps, engineers designed layouts that allowed liquids to move naturally through successive stages of production. This required an understanding of gradients, flow rates, storage capacity, and hydraulic behavior. Some industrial complexes covered several hectares and processed thousands of tons of material annually. Their hydraulic sophistication rivals certain mining operations of later centuries. Yet no detailed engineering manuals survive. The physical structures remain, but the design logic behind them often does not. One of the most unusual aspects of alum production involved an ingredient found in virtually every community: human urine. Historical records indicate that urine was collected and incorporated into stages of the manufacturing process. To modern observers, this seems bizarre, but chemically it makes sense. Urine contains ammonia-producing compounds that influence reactions within processing solutions. The remarkable detail is that workers recognized its usefulness centuries before modern biochemistry explained why it worked. Communities sometimes participated in collection programs supplying industrial facilities with raw materials. This created a chemical supply chain based on empirical observation rather than scientific understanding. People knew the method worked, but few could explain the underlying chemistry. Yorkshire's alum industry operated on a vast scale. Millions of tons of shale were quarried, transported, burned, washed, and refined long before modern machinery existed. Workers extracted rock from coastal cliffs, moved it across difficult terrain, maintained burning heaps and hydraulic systems, and processed chemical solutions. The ruins reveal the industry's immense scale, but many details of how it functioned remain unknown. How do you think the first producers discovered that Yorkshire shale could be transformed into alum without modern science? Alinda is an ancient city located in the Aydın province of southwestern Turkey, in the historic region of Caria. Built on steep hills overlooking fertile valleys, the site occupies a strategic position roughly 30 kilometers from the ancient city of Milisa. The ruins were first systematically documented by European explorers during the 19th century and later investigated by archaeologists studying Hellenistic urban development in Anatolia. Today, massive fortification walls, reservoirs, towers, streets, and one of the best preserved agoras in Asia Minor remain visible. Yet the greatest mystery is not what survives. It is how an ancient civilization managed to build and maintain such a sophisticated mountain city more than 2,000 years ago. The first mystery appears immediately upon entering Alinda. The city was protected by enormous defensive walls, extending across steep rocky slopes. Some surviving sections remain several meters high and hundreds of meters long. The walls follow irregular terrain with remarkable precision, adapting to cliffs, ridges, and natural obstacles while maintaining defensive effectiveness. Modern engineers understand how stone fortifications work, but the mystery is how ancient builders achieved such large-scale construction in terrain that remains difficult even for modern machinery. Archaeologists estimate that many individual stone blocks weigh several tons. Thousands of these blocks were quarried, transported uphill, shaped and positioned with extraordinary accuracy. Comparisons are often made with the fortifications of Pergamon and Machu Picchu. both sites demonstrate sophisticated adaptation to mountainous environments. Yet Alinda remains unusual because nearly the entire urban landscape was integrated into a defensive mountain system. No ancient engineering manuals survive to explain exactly how the builders organized transportation, labor management, surveying, and construction logistics on such difficult terrain. The walls remain, the methods do not. Most ancient cities developed on relatively flat ground. Alinda did not. The city was constructed across multiple elevation levels connected by terraces, retaining walls, roads, and stairways. Entire neighborhoods were effectively carved into the mountain itself. This required an understanding of geology and topography far beyond simple construction. Modern urban engineers use slope analysis, soil testing, and computer simulations before building on steep terrain. Ancient builders possessed none of these tools, yet Alinda remained occupied for centuries. Researchers continue to study how its planners calculated drainage, stabilized slopes, distributed weight across terraces, and minimized erosion. The city demonstrates a level of environmental adaptation that appears remarkably advanced for its era. Many of the retaining structures still function today despite more than 2 millennia of weathering, earthquakes, and seasonal rainfall. The precision of the planning suggests knowledge accumulated through generations of practical engineering experience. Exactly how that knowledge was transmitted remains unknown. Water represented the greatest challenge for any mountain settlement. Without a reliable supply, Alinda could never have survived. Excavations have revealed reservoirs, cisterns, channels, and hydraulic installations distributed throughout the city. These systems collected rainfall, stored water, and distributed it to residents living at different elevations. The mystery lies in scale. A substantial urban population requires enormous quantities of water. Modern estimates suggest that even modest ancient cities needed tens of thousands of litres daily for drinking, food preparation, sanitation, workshops, and military use. Researchers believe Alinda relied heavily on sophisticated rainwater harvesting systems. However, the complete hydraulic network remains only partially understood. This places Alinda among a select group of ancient sites whose water technologies continue to puzzle archaeologists, including Petra, Machu Picchu, and Masada. In each case, ancient engineers developed solutions to environmental challenges that modern researchers are still attempting to fully reconstruct. The surviving reservoirs demonstrate that the system worked. The complete design remains elusive. Among Alinda's most impressive structures stands its enormous agora. The building stretches approximately 95 meters in length and is considered one of the best preserved Hellenistic market complexes in Anatolia. At first glance, it appears to be merely a commercial structure. Closer inspection reveals a significant engineering challenge. The entire complex was constructed on uneven mountainous terrain while maintaining structural stability across a large footprint. The builders needed to create level surfaces, support substantial loads, manage drainage, and ensure long-term durability. Modern architects routinely perform complex calculations before constructing large public buildings. Ancient builders relied on geometry, observation, and practical experience. The fact that major portions of the structure survive after more than 2,000 years demonstrates that their calculations were remarkably effective. Researchers continue to debate the precise construction methods used to achieve such stability. Southwestern Anatolia lies within an active seismic region. Throughout its history, Alinda would have experienced numerous earthquakes ranging from minor tremors to major destructive events. Yet significant portions of the city remain standing. This has led some researchers to investigate whether ancient builders unintentionally developed forms of earthquake-resistant construction. Large stone blocks possess enormous mass, while carefully fitted masonry can sometimes dissipate seismic energy more effectively than rigid structures. Similar observations have been made at sites such as Sacsayhuaman in Peru and certain Greek fortifications throughout the Mediterranean. Whether Alinda's resilience resulted from deliberate engineering or accumulated construction experience remains uncertain. What is clear is that many structures survived conditions that destroyed countless younger buildings. The city appears to embody principles of structural durability that are not yet fully understood. Ancient ruins often conceal the most important engineering achievement: logistics. Every wall, tower, reservoir, and public building required raw materials, labor, food, tools, planning, and transportation. Archaeologists estimate that constructing Alinda required moving tens of thousands of tons of stone without cranes, engines, trucks, or modern lifting equipment. The workforce needed to quarry stone, transport materials, manufacture tools, prepare foundations, and coordinate construction activities would have been enormous. Comparisons can be drawn with large-scale projects throughout the Hellenistic world. Yet, the administrative systems that organized these efforts are largely invisible in the archaeological record. How many workers participated? How were they supplied? How long did construction take? How were resources allocated? The ruins provide evidence of success, but the organizational mechanisms behind that success remain largely hidden.